Unit 3 Chemical Kinetics, Unit 4 D and F Block Elements, Unit 5 Coordination Compounds। ये सारे के सारे चैप्टर्स इस सिंगल वीडियो में करने वाले हैं दोस्तों। तो पहला चैप्टर है सॉल्यूशन। इसमें कुछ 1.1 में पढ़ेंगे टाइप ऑफ सॉल्यूशन, सेकेंड में एक्सप्रेसिंग कंसंट्रेशन ऑफ सॉल्यूशन, एंड 1.3 में सॉल्युबिलिटी, 1.4 वेपर प्रेशर ऑफ लिक्विड सॉल्यूशन, 1.5 आइडियल एंड नॉन आइडियल सॉल्यूशन, 1.6 colligative properties and determination of molar mass, 1.7 abnormal molar mass सॉल्यूशन में करेंगे। इलेक्ट्रोकेमिस्ट्री में इलेक्ट्रोकेमिकल सेल्स, गैल्वेनिक सेल्स, नस्ट इक्वेशन, कंडक्टेंस ऑफ इलेक्ट्रोलाइटिक सॉल्यूशन, इलेक्ट्रोलाइटिक सेल एंड इलेक्ट्रोलाइसिस, बैटरीज, फ्यूल सेल्स एंड कोरोजन करेंगे। उसके बाद केमिकल काइनेटिक्स में रेट ऑफ केमिकल रिएक्शंस, factors influencing rate of reaction, integrated rate equation, temperature dependence of rate of equation, collision theory of a chemical reaction करेंगे। उसके बाद डी एंड एफ ब्लॉक में पोजीशन ऑफ इन द पीरियोडिक टेबल, इलेक्ट्रॉनिक कन्फिग्रेशन ऑफ डी ब्लॉक एलिमेंट्स, जनरल प्रॉपर्टी ऑफ द ट्रांजिशन एलिमेंट डी ब्लॉक एलिमेंट्स, some important compounds of transition elements, the lanthanoids, the actinoids, some application of D and F blocks करना है। उसका कोऑर्डिनेशन कंपाउंड में वर्नर थ्योरी ऑफ कोऑर्डिनेशन कंपाउंड्स, डिफिनीशन ऑफ सम इम्पॉर्टेंट टर्म परटेनिंग टू कोऑर्डिनेशन कंपाउंड्स, नोमेनक्लेचर ऑफ कोऑर्डिनेशन कंपाउंड्स, आइसोमेरिज्म इन कोऑर्डिनेशन कंपाउंड्स, बॉन्डिंग इन कोऑर्डिनेशन कंपाउंड्स, बॉन्डिंग इन मेटल कार्बोनाइल्स, इम्पॉर्टेंस ऑफ एप्लीकेशन ऑफ कोऑर्डिनेशन कंपाउंड। सो दोस्तों 5 यूनिट्स हैं, इन सारे को एक सिंगल वीडियो में करना है। और कितने टाइम लेंगे, चलो लेट्स गो स्टार्ट। तो यूनिट 1 है सॉल्यूशन। सो लेट almost all process in our body occur in some kind of liquid solution. In normal life we rarely come across pure substances. Most of these are mixture of containing 2 or more pure substances. Their utility or importance in life depends on their compositions. For example, the properties of the brass mixture of copper and zinc are quite different from those German silver mixture of copper and zinc and nickel, or bronze mixture of copper and tin. 1 part per million ppm of fluorides ion in water prevent tooth decay, while 1.5 ppm causes the tooth become mottled, and highly concentrated of fluoride ion can be poisonous. For example, sodium fluoride is used in rat poison. Intravenous injection are always dissolved in water containing salt at particular ionic concentration that match with blood plasma concentration, and so on. In this unit, we will consider mostly liquid solution and their formation. This will be followed by studying properties of the solution like vapor pressure and colligative properties. We will begin with type of solution and then various alternatives in which concentration of solute can be expressed in liquid solution. 1.1 Type of solution. Solution are homogeneous mixture of 2 or more than 2 components. By homogeneous mixture we mean that its composition and properties are uniform throughout the mixture. Generally, the component that is present in largest quantity is known as solvent. Solvent determine the physical state in which solution exists. One or more components present in solution other than solvent are called solutes. In this unit, we shall consider the binary solution, that is consisting of 2 components. Here each component may be solid, liquid, or in gaseous state and are summarized in table 1.1. 1.1 Type of solution. First type of solution, gaseous solution. Solute, gas, liquid, or solid. If solvent is gas, then common examples are mixture of oxygen and nitrogen gases. If solvent gas, chloroform mixes nitrogen gas. And if solute is solid and solvent is gas, then camphor in nitrogen gas. Liquid solution, solute is gas and solvent is liquid, like oxygen dissolved in water, and liquid solute and solvent is liquid, then ethanol is dissolved in water. And if solute is solid, and solvent is liquid. Its example is glucose dissolved in water. Solid solution example, solute is gas and solvent is solid. Then example is solution of hydrogen in palladium, and solid is liquid and solvent is solid, amalgam of mercury with sodium. And if solute is solid and solvent is solid, its example is copper dissolved in gold. 1.1 expressing concentration of solution. Composition of solution can be described by expressing its concentration. The latter can be expressed either qualitatively or quantitatively. For example, qualitatively we can say that the solution is dilute, that is relatively very small quantity of solute, or it's concentrated, that is relatively very large quantity of solute. But in real life this kind of description can aid to a lot confusion, and thus the need of quantitative description of the solution. There are several ways by which we can describe concentration of solution quantitatively. First, mass percentage, weight by weight. The mass percentage of component of a solution is defined as mass percent of a component is equal to mass of the component in solution by total mass into 100. For example, if a solution is described by 10% glucose in water by mass, it's mean that 10 gram of glucose is dissolved in 90 gram of water, resulting in a 100 gram solution. Concentration described by mass percentage is commonly used in industrial chemical applications. For example, commercial bleaches solution contain 3.62 mass of percent of sodium hypochlorite in water. Second, volume percentage, volume by volume. The volume percent is described as volume percent of a component is equal to volume of component by total volume of solution into 100. For example, 10% ethanol solution in water means that 10 ml of ethanol is dissolved in water such that the total volume of solution is 100 ml. Solution containing liquid are commonly expressed in this unit. For example, 35% volume by volume solution of ethylene glycol in antifreeze is used in car for cooling the engine. At this concentration, the antifreeze lowers the freezing point of water to 255.4 Kelvin minus 17.6 degrees Celsius. Third, mass by volume percentage. Another unit which is commonly used in medicine and pharmacy is mass by volume percentage. It is mass of solute dissolved in 100 ml of solution. 4. Parts per million. When a solute is present in trace quantity, it convenience to express concentration in parts per million ppm, and defined as parts per million is equal to number of parts of component by total number of parts of all component of solution into 10 to the power 6. As in case of percentage, the concentration in parts per million can also be expressed as mass to mass, volume to volume, and mass to volume. A liter of sea water weight 1030 gram contain about 6 into 10 per minus 3 gram of dissolved oxygen O2. Such a small concentration is also expressed as 5.8 gram per 10 to the power 6 gram, 5.8 ppm of seawater. The concentration of pollutants in water or atmosphere is often expressed in terms of microgram per ml or ppm. Fifth, mole fraction. Commonly used symbol for mole fraction is X, and subscript used on the right hand side of X denote the components. It's defined as mole fraction of component is equal to number of moles of component by total number of moles of all components. For example, in binary mixture, if number of moles of A and B are Na and Nb, the mole fraction of A is Xa is equal to Na by Na plus Nb. For example, containing for a solution containing I mole of a component, we have Xi is equal to Ni by N1 plus N2 plus Ni, and this expresses this means Ni upon summation of Ni ones to लेकर I. It can be shown in given solution. Sum of all mole fraction is unity, that is x1 plus x x2 plus dot 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 xi is equal to 1. Mole fraction unit is very useful in relating some physical properties of solution. Say vapor pressure with concentration of the solution, and quite useful in describing calculation involving gas mixture. For molarity. Molarity M defined as number of moles of solute dissolved in 1 liter or 1 cubic decimeter of solution. Molarity is equal to mole of solute. Molarity is equal to mole of solute by volume of solution. For example, 0.25 mole per liter or 0.25 molar solution of NaOH means 0.25 mole of NaOH dissolved in 1 liter of or 1 cubic decimeter. For molality. Molality M defined as number of moles of solute per kg of solvent and expressed as molality is equal to mole of solute by mass of solvent in kg. For example, 1 mole per kg, 1 molar solution of KCl means that 1 mole 74.5 gram of KCl dissolved in 1 kg of water. Each method of expressing concentration of the solution has its own merits and demerits. Mass percent, ppm, mole fraction and molality are independent of temperature, whereas molality is a function of temperature. This is because volume depends on temperature and the mass does not. 1.3 Solubility. Solubility of a substance is its maximum amount that can be dissolved in a specified amount of solvent at a specified temperature. It depends upon nature of solute and solvent as well as temperature and pressure. Let us consider the effect of this factor in solution of a solid or a gas in a liquid. 1.3.1 Solubility of solid in a liquid. Every solid does not dissolve in given liquid, while sodium chloride and sugar dissolve readily in water. Naphthalene and anthracene do not. On the other hand, naphthalene and anthracene dissolve readily in benzene, but sodium chloride and sugar do not. It is observed that polar solute dissolve in polar solvent and non-polar solute in non-polar solvent. In general, solute dissolve in solvent if the intermolecular interactions are similar in two, or we may say like dissolve like. When solute is added to solvents, some solute dissolve and its concentration increases in solution. This process is known as dissolution. Some solute particle in solution collide with solute particle and get separated out of solution. This process is known as crystallization. A stage is reached when the two processes occur at the same rate. Under such condition, number of solute particles going into solution will equal to solute particles separating out, and a state of dynamic equilibrium is reached. Solute plus solvent form solution. At this stage, the concentration of solute in solution will remain constant under given condition, that is temperature and pressure. Similar process is followed when gases are dissolved in liquid solvents. Such a solution is in which no more solute can be dissolved at the same temperature and pressure is called a saturated solution. An unsaturated solution is one in which more solute can be dissolved at the same temperature. This solution, which is in dynamic equilibrium with undissolved solute, is the saturated solution and contains the maximum amount of solute dissolved in given amount of solvent. Thus, the concentration of solute is in such solution is its solubility. Earlier, we have observed that solubility of one solute into another depends on nature of substances. In addition to these variables, two other parameters, that is temperature and pressure, also control this phenomena. Effect of temperature. The solubility of solid in a liquid significantly affected by temperature changes. Consider the equilibrium represented by equation 1.10. This being dynamic equilibrium must follow Le-Chatelier principle. In general, if in a nearly saturated solution, the dissolution This solution process is endothermic. Delta solution H is equal to greater than 0. The solubility should increase with rise in temperature, and if exothermic, the solubility should decrease. These trends are also observed experimentally. Effect of pressure. Pressure does not have any significant effect on solubility of solid in liquid. It is so because solids and liquids are highly incompressible and practically remain unaffected by change in pressure. 1.3.2 Solubility of gas in a liquid. Many gases dissolve in water. Oxygen dissolves only to a small extent in water. It is this dissolved oxygen which sustains all aquatic life. On the other hand, hydrogen chloride gas HCl is highly soluble in water. Solubility of gases in liquid is greatly affected by pressure and temperature. The solubility of gases increases with increase in pressure. For solution of gases in a solvent, consider a system as shown in figure 1.1a. The lower part is solution and the upper part is gaseous system at pressure P and temperature T. Assume this system to be in a state of dynamic equilibrium, that is, under the condition rate of gaseous particle entering and leaving the solution phase is the same. Now increase in pressure over solution phase by compressing the gas that smaller volume. This will increase the number of gaseous particles per unit volume over the solution and also the rate at which gaseous particles are striking the surface of solution to enter it. The solubility of gas will increase until the new equilibrium is reached, resulting in an increase in pressure of gases above the solution and thus solubility increase. Henry was the first to give a quantitative relation between pressure and solubility of gas in solvent, which is known as Henry law. The Henry stated that at constant temperature, the solubility of gas in liquid directly proportional to the partial pressure of gas present above the surface of the liquid or solution. Dalton, a contemporary of Henry, also concluded independently that the solubility of gas in a liquid solution is a function of partial pressure of the gas. If we use mole fraction of a gas in the solution as measure of solubility, then it can be said to be mole fraction of gas in a solution is proportional to the partial pressure of gas over the solution. The most commonly used for Henry law states that the partial pressure of gas in vapor phase P is proportional to the mole fraction of gas X in solution, as expressed as K is directly proportional to K into partial pressure of gas X. Figure 1.1 Effect of pressure and solubility of gas. The concentration of dissolved gas is proportional to pressure on the gas above the solution. Here kh is Henry law constant. If we draw a graph between partial pressure of gas versus mole fraction of gas in solution, then we should get a plot of type figure 1.2. 1.2 Experimental result for the solubility of HCl gas in cyclohexane at 293 Kelvin. The slope of line is Henry constant kh. So mole fraction, and this is partial pressure, and this is slope gives Henry constant kh. Slope is equal to kh, Henry constant. Different gases have different kh value at the same temperature. This suggests that kh is a function of nature of gas. It is obvious from equation 1.11 that higher the value of kh at given pressure, the lower the solubility of gas in a liquid. It can be seen from table 1.1 that kh value of both N2 and O2 increases with increase in temperature, indicating that solubility of gas increases with decrease in temperature. It is due to the reason that aquatic species more comfortable in cold water rather than warm water. Value of Henry gas constant for some selected gases in water. So these are Henry temperature, and these are KH, and these are gases. So at 293 Kelvin मैक्सिमम KH हेनरी कांस्टेंट किसका है भाई? तो सबसे ज़्यादा हेनरी कांस्टेंट N2 है, मीन्स ये ज़्यादा रेडली डिजॉल्व हो जाएगा वाटर में. Henry law finds several applications in industry and explains some biological phenomena. Notable among these are: first, to increase the solubility of carbon dioxide in soft drink and soda water, the bottle is sealed under high pressure. Second, scuba divers must cope with high concentration of dissolved gases while breathing air at high pressure underwater. Increased pressure increases the solubility of atmospheric gas in blood. When the divers come toward the surface, the pressure gradually increases. This releases dissolved gases and led to formation of bubbles of nitrogen in blood. This block the capillaries and create medical condition known as bends, which painful and dangerous for life. To avoid bends as well as the toxic effect of high concentration of nitrogen in blood, the tank used by scuba diver is filled with diluted helium, 11.7% helium, 56.2% nitrogen, and 32% oxygen. At high altitude, the partial pressure of oxygen is less than that at the ground levels. This led to low concentration of oxygen in the blood and tissue of people living in high altitude or climbers. Low blood oxygen caused climbers to become weak and unable to think clearly. Symptoms of condition known as anoxia. Effect of temperatures. Solubility of gases in liquid decreases with rise in temperature. When dissolved, the gas molecules are present in liquid phase, and the process of dissolution can be considered similar to condensation, and heat is evolved in this process. We have learned in last section that dissolution process involve dynamic equilibrium and thus must follow Le Chatelier principle. As dissolution is an exothermic process, the solubility should decrease with increase in temperature. 1.4 Vapor pressure of liquid solution. Liquid solutions are formed when solvent in a liquid. The solute can be a gas, a liquid, or solid. Solution of gas in a liquid have already been discussed in section 1.3.2. In this section, we shall discuss the solution of liquids and solids in a liquid. Such solution may contain one or more volatile components. Generally, the liquid solvent is volatile. The solute may or may not be volatile. We shall discuss the properties of only binary solution. That is, the solution containing two components, namely the solution first, liquid in liquid, and second, the solid in liquid. 1.4.1 Vapor pressure of liquid solution. Let us consider binary solution of two volatile liquid and denote the two components as 1 and 2. When taken in closed vessel, both the components would evaporate and eventually equilibrium would be stabilized between vapor phase and liquid phase. Let the total vapor pressure at this stage is P total, and P1 P2 be the partial vapor pressure of two components 1 and 2 respectively. These partial pressures are related to mole fraction x1 and x2 of the two component 1 and 2 respectively. The French chemist Brancois Martin Rolt in 1886 gave the quantitative relationship between them. The relationship is known as Rolt's law, which states that for a solution volatile liquid, the partial vapor pressure of each component of solution is directly proportional to its mole fraction present in a solution. Thus, component 1 partial pressure directly proportional to x1 and P1 directly corresponds to P1 naught x1, where P1 naught is vapor pressure of pure component 1 at the same temperature. Similarly, for component 2, P2 is equal to P2 naught x2. At P2 naught represent the vapor pressure of pure component 2. According to Dalton law of partial pressure, the total pressure P total over solution phase container will be sum of all the partial pressure of components of solution and given as P total is equal to P1 plus P2. Substituting the value of P1 and P2, we get P total is equal to x1 P1 naught plus x2 P2 naught, and 1 minus x2 P1 naught plus x2 P2 naught. P total is equal to P1 naught plus P2 minus P1 naught x2. Following conclusion can be drawn from equation 1.16. First, total volume pressure over solution can be related to mole fraction of any one component. Second, total vapor pressure over solution varies linearly with the mole fraction of component 2. Third, depending on the vapor pressure of pure component 1 and 2, total vapor pressure over the solution decreases with the increased mole fraction of the component first. A plot of P1 and P2 versus mole fraction x1 and x2 for solution gives a linear plot as shown in figure 1.3. These lines 1 and 2 pass through the points for which x1 and x2 are equal to unity. Similarly, the plot lines third of total P total versus x2 is also linear. The minimum value of P total is P1 and maximum value of P2 naught, assuming that component 1 is less than volatile than 2, that is P2 greater than P1. The composition of phase in equilibrium with solution determined by the partial pressure of components. If y1 and y2 are mole fraction of component 1 and 2 respectively, the vapor phase, then using Dalton law of partial pressure, P1 is equal to y1 P total and P2 is equal to y2 P total. In general, P1 is equal to P1 P total. One point three, the plot of vapor pressure and mole fraction of ideal solution at constant temperature. The dashed line 1 and 2 represent the partial pressure of the component. It can be seen from plot P1 and P2 directly proportional to x1 and x2 respectively. The total vapor pressure is given by line marked third in the given figure. So these are mole fraction, these are vapor pressure. This is P naught and here is P2 third. In general, Py is equal to Py P total. 1.4.2 Raoult's law as a special case of Henry law. According to Raoult's law, the vapor pressure of volatile components in a given solution is given by Pi is equal to xi Pi1 xi Pi naught. In the solution of gas in a liquid, one of the component is so volatile that it exists as a gas, and we have already seen that its solubility is given by Henry law, which states as P is equal to kHx. If we compare the equation of Raoult's law and Henry law, it can be seen that the partial pressure of volatile component of gas is directly proportional to its mole fraction in solution. Only the proportionality constant kH differ from P1 naught. Thus, Raoult's law become a special case of Henry law in which kH become equal to P1 naught. 1.4.3 Vapor pressure of solution of solid in liquid. Another important class of solution consists of solid dissolved in liquid. For example, sodium chloride, glucose, urea, and cane sugar in water and iodine sulfur dissolved in carbon disulfide. Some physical properties of this solution are quite different from those of pure solvents. For example, the vapor pressure liquid at a given temperature vaporize, and under equilibrium condition the pressure exerted by vapor of liquid over liquid phase is called vapor pressure. In a pure liquid, the entire surface is occupied by molecules of the liquid. If a non-volatile solute is added to solvent to give a solution, the vapor pressure of a solution is solely from the solvent alone. This vapor pressure of the solution at given temperature is found to be lower than the vapor pressure of the pure solvent at same temperature. In the solution, the surface has both solute and solvent molecule. Thereby, the fraction of the surface covered by solvent molecule get reduced. Consequently, the number of solvent molecule escaping from the surface is corresponding reduced. Thus, the vapor pressure is also reduced. The decrease in vapor pressure of solvent depends on the quantity of non-volatile solute present in a solution, irrespective of its nature. For example, decrease in vapor pressure of water by adding 1 mole of sucrose to 1 kg of water nearly similar to that produced by adding 1 mole of urea to same quantity of water at the same temperature. Raoult's law in general form can state that for any solution of partial vapor pressure of each volatile component in a solution is directly proportional to its mole fraction. In binary solution, let us denote the solvent by 1 and solute by 2. When the solute is non-volatile, only the solvent molecule are present in vapor phase and contribute to vapor pressure. Let P1 be vapor pressure and the solvent X1 be the mole fraction. Pi not be its vapor pressure in pure state. Then, according to Raoult's law, P1 is equal to P1 directly proportional to X1 and P1 is equal to X1 P1 naught. The proportionality constant is equal to vapor pressure of pure solvent P1 naught. A plot between vapor pressure and mole fraction of solvent in linear figure 1.15. Here is mole fraction X solvent and this is vapor pressure. Figure 1.4, decrease in vapor pressure of the solvent on account of the presence of solute in solvent. A. Evaporation of the molecule of solvent from its surface is denoted by this blue dot, and B. A solution solute particle have been denoted by this green dot, and they also occupy part of that surface. (1.5) Ideal and non-ideal solution. Liquid solution can be classified into ideal and non-ideal solution on the basis of Raoult's law. 1.5.1 Ideal solution. The solution which obey Raoult's law over the entire range of the concentration are known as ideal solution. The ideal solution have two components important properties. The enthalpy of mixing of the pure component to form solution is 0 and the volume of mixing is also 0, that is delta H mixture is equal to 0 and delta mix volume is equal to 0. It means no heat absorbed or evolved when the components are mixed. Also, the volume of solution would be equal to the sum of the volume of two components. At molecular level, the ideal behavior of the solution can be explained by considering two components A and B. In pure component, the intermolecular attractive interaction will be type AA and BB, whereas the binary solution is addition of these two interactions. AB type of interaction will also be present. If the intermolecular attractive force between AA and BB are nearly equal to those AB, this led to formation of ideal solution. A perfectly ideal solution is rare, but some solutions are nearly ideal in behavior. Solution of n-hexane and n-heptane bromoethane and chloroethane benzene and toluene fall in this category. 1.5.2 non-ideal solution. When a solution does not obey Raoult's law over the entire range of the concentration, then it is called non-ideal solution. The vapor pressure of such solution is either higher or lower than that of predicted by Raoult's law. If its higher solution exhibits positive deviation and is lower, it exhibits negative deviation from Raoult's law. The plots vapor pressure as function of mole fraction for such solution is shown in figure 1.6. The cause of this deviation lie in the nature of interaction at the molecular level. In case of positive deviation from Raoult's law, EV interactions are weaker than those between AA or BB. That is, in this case, the intermolecular attractive force between the solid-solvent molecule are weaker than those between the solute and solvent-solvent molecules. This means that in case of solution, the molecule A or B will be find easier to escape than in pure state. This will increase the vapor pressure and result in positive deviation. Mixture of ethanol and acetone behave in this manner. In pure ethanol, the molecules are hydrogen bonded. On adding acetone, its molecules get in between host molecule and break some hydrogen bond between them. Due to weakening of interaction, the solution show positive deviation from Raoult's law. In solution found by adding carbon disulfide to acetone, the bipolar interaction between solute-solvent molecule are weaker than respective interaction among the solute-solute and solvent-solvent molecules. This solution also shows positive deviation. Vapor pressure of two system components system as a function of composition. A solution that shows positive deviation from Raoult's law. B a solution shows negative deviation from Raoult's law. So this is graph of positive deviation and this is graph of negative deviation. This is mole fraction and this is vapor pressure. In case of negative deviation from Raoult's law, intermolecular attractive force between AA and BB are weaker than those between AB and led to decrease in vapor pressure, resulting in negative deviation. An example of this type of mixture of phenol and aniline. In this case, the intermolecular hydrogen bonding between phenolic proton and lone pair of on nitrogen atom from aniline is stronger than the respective intermolecular hydrogen bonding between similar molecules. Similarly, a mixture of chloroform and acetone form a solution with negative deviation from Raoult's law. This is because chloroform molecule is able to form hydrogen bond with the acetone molecule as shown in figure. This decrease in escaping tendency of molecule for each component are consequently vapor pressure decrease resulting in negative deviation from Raoult's law. Some liquid on mixing form azeotrophs, which are binary mixture having the same composition in liquid and vapor phase and boil at a constant temperature. In such cases, it is not possible to separate the component by fractional distillation. This is the two types of azeotroph called minimum boiling azeotrophs and maximum boiling azeotrophs. The solution which show a large positive deviation from Raoult's law for minimum boiling azeotroph at specific composition. For example, ethanol water mixture obtained by fermentation of sugar on fractional distillation give containing approximately 95% by volume of ethanol. Once this composition is known as azeotroph composition has been achieved, the liquid and vapor have the same composition and no further separation occurs. The solution that shows large negative deviation from Raoult's law form maximum boiling azeotroph at specific composition. Nitric acid and water is an example of such this class azeotroph. This azeotroph has the approximate composition 68% nitric acid and 32% water by mass with boiling point 393.5 K. 1.6 colligative property and determination of molar mass. We have learned in section 1.4.3 that the vapor pressure of solution decreases with a non-volatile solution is added to a volatile solvent. There are many properties of solution which are connected with this decrease in vapor pressure. These are: first, relative lowering of vapor pressure of solvent; second, depression in freezing point of the solvent; third, elevation of boiling point of the solvent; and fourth is osmotic pressure of solution. All these properties depend on the number of solute particles irrespective of their nature related to total number of particles present in the solution. Such properties are called colligative properties. Colligative from Latin co means together, liger means to bind. In this following section, we will discuss these properties one by one. 1.6.1 Relative lowering of vapor pressure. We have learned in section 1.4.3 that vapor pressure of solvent in solution is less than that of a pure solvent. Raoult's law established that the lowering of vapor pressure depends only on concentration of the solute particle and it is independent of their identity. The equation 1.20 given in section 1.43 establishes a relation between vapor pressure of the solution, mole fraction of and vapor pressure of solvent. P1 is equal to x1 P1 naught. The reduction in vapor pressure of solvent delta P1 is given as P1 is equal to P1 naught 1 minus x1, knowing that x2 is equal to 1 minus x1 in equation 1.23 reduced. Delta P1 is equal to x2 P1 naught. In solution containing several non-volatile solutes, the lowering of vapor pressure depends on the sum of mole fraction of different solutes. Equation 1.24 can be written as delta P1 by P1 naught is equal to P1 minus P1 by P1 naught is equal to x2. The expression on the left side of equation as mentioned earlier, the relative lowering of vapor pressure and equal to the mole fraction of the solute. The above equation can be written as P1 naught minus P1 by P1 naught is equal to N2 by N1 plus N2. X2 is equal to N2 by N1 plus N2. Here N2 and N1 and N2 are the number of moles of solvent and solute respectively present in solution. For dilute solution, N1 is very greater than N2, hence neglecting N2 is in the denominator, we get N1 P1 minus P2 by P1 naught is equal to N2 by N1, or P1 naught minus P1 by P1 naught is equal to W2 into M1 by M2 into W1, where W and W2 are masses and M1 and M2 are molar masses of solvent and solute respectively. From equation 1.28, knowing all other quantities, the molar mass of solute M2 can be calculated. 1.6.2 Elevation in boiling point. The vapor pressure of liquid increases with increase of temperature. It boils at the temperature at which the vapor pressure is equal to the atmospheric pressure. For example, water boils at 373.15 Kelvin 100 degrees Celsius. Because at this temperature the vapor pressure of water is 1.013 bar 1 atmosphere. We also learned in the last section of vapor pressure of solvent decreases in the presence of non-volatile solute. Figure 1.7 depicts the variation of vapor pressure of pure solvent and solution as a function of temperature. For example, the vapor pressure of an aqueous solution of sucrose is less than 1.013 bar at 373.15 Kelvin. In order to make this solution boil, the vapor pressure must be increased to 1.013 bar by raising the temperature above boiling temperature of pure solvent or water. Thus, the boiling point of solution is always higher than that of boiling point of pure solvent in which the solution is prepared, as shown in figure 1.7. Similarly, the lowering of vapor pressure, the elevation of boiling point also depends on the number of solute molecules rather than their nature. A solution of 1 mole of sucrose in 100 gram of water boils at 373.52 Kelvin at 1 atmospheric pressure. Let Tb naught be the boiling point of pure solvent and Tb be the boiling point of solution. The increase in the boiling point delta Tb is equal to Tb minus Tb naught is also known as elevation in boiling point. Experiments have shown that for dilute solution, the elevation in boiling point delta Tb is directly proportional to molar concentration of solute in a solution. Thus, delta Tb directly proportional to molality and delta Tb directly proportional to Kb Here is graph. The molar pressure of curve for solution lies below the curve for pure water. The diagram shows delta Tb denotes the elevation of boiling point of solvent. Here is temperature and here vapor pressure. So this is solution and this is solvent. After adding solute, vapor pressure decreases. Here molality in the number of moles of solute dissolved in 1 kg of solvent and constant proportionality. Kb is the boiling point elevation constant or molar elevation constant, ebullioscopic constant. The unit of Kb is Kelvin kg per mole. Values of Kb for some common solvent are given table 1.3. If W2 gram of solute of molar mass M2 is dissolved in W1 gram of water, then molality M of solution is given as molality is equal to W2 by M2 by W1 into by 1000 is equal to 1000 in W2 by W2 into W1. Substituting the value of molality in equation 1.30, we get delta Tb is equal to Kb into 1000 by W2 by M2 into W1. M2 is equal to 1000 in W2 into Kb by delta Tb into W1. Thus the order of determine M2 molar mass of solute, also mass of solute is known as mass of solvent is taken, and delta Tb is determined experimentally known as solvent whose Kb value is known. 1.6.3 depression in freezing point. Lowering the vapor pressure of solution causing lowering of the freezing point compared to that of pure solvent. We know that the freezing point of substances of solid is in dynamic equilibrium with liquid solid phase. Thus, the freezing point of substance may be defined as the temperature at which the vapor pressure of the substances in its liquid phase is equal to its vapor pressure in the solid phase. A solution will freeze when its vapor pressure is equal to the vapor pressure of pure solid solvent, as in clear in figure 1.8. According to Raoult's law, when a non-volatile solid is added to solvent, its vapor pressure decreases and now its would become equal to the solid solvent at lower temperature. Thus the freezing point of the solvent decreases. Let Tf naught be the freezing point of pure solvent and Tf be its freezing point when non-volatile solute is dissolved in it. The decrease in freezing point as delta Tf is equal to Tf naught minus Tf is known as depression in freezing point. Diagram showing delta Tf depression in freezing point of a solvent in a solution, and this is temperature and this is vapor pressure. Frozen solvent, liquid solvent, and this is solution. And this is delta change in temperature in freezing point. Similarly, the elevation of boiling point, depression of freezing point, delta Tf for dilute solution, ideal solution is directly proportional to molality M of solution. Thus, delta Tf directly proportional to molality, or delta Tf direct is equal to Kf into molality. The proportionality constant Kf, for which depend on the nature of solvent, is known as freezing point depression constant or molar depression constant or stereoscopic constant. The unit of Kf is Kelvin kg per mole. Values of Kf for some common solvent are listed in table 1.3. If W2 gram of solute having molar mass as M2 present in W1 gram of solvent produce the depression in freezing point delta Tf of the solvent, then molality of solute is given in equation 1.13. Molality is equal to W2 by M2 by W1 into 1000. Substituting this value of molality in equation 1.34, we get delta TF is equal to Kf into W2 by W M2 by W1 by 1000, or delta 2 is equal to Kf W2 into 1000 by M2 into W1. M2 is equal to Kf into W2 into 1000 by delta T of W1. Thus, determining the molar mass of solute, we should know the quantity of W1, W2 and delta T of weight, along with the molar freezing point of depression constant. The value of Kf and Kv depends upon the nature of solvent, can be ascertained from the following equation. Kf is equal to R into M1 into delta into Tf to the square by 1000 into delta heat of fusion. K boiling constant is equal to R into M1 into Tb square by 1000 into delta vaporization heat of vaporization. Hence, the symbol R and M1 stand for gas constant and molar mass of solvent. Respective Tf and Tb denote freezing point and boiling point of pure solvent, respectively in Kelvin. Further, delta fusion H and delta vapor H represent the enthalpy for the fusion of vaporization of solvent, respectively. Boiling point in Kelvin, freezing point, and Kf values. 1.6.4 Osmosis and osmotic pressure. There are many phenomena which is observed in nature at home. For example, raw mangoes shrivel when pickled in brine salt water, wilted flower revive when placed in fresh water, blood cells collapse when suspended in saline water, etc. If we look into this process, we find one thing common in all, that is, all of these substances are bound by membranes. These membranes can be of animals or vegetable origin, and these occur naturally, such as pig bladders, or parchment can be synthetic, but such as cellophane. These membranes appear to be continuous sheet or films, yet they contain network of microscopic holes or pores. Figure 1.9, level of solution rises in thistle funnel due to osmosis of solvent. So this is height is equal to rho Hg, and this is solvent and this is solution. This is semi-permeable membrane. A small solvent molecule like water can pass through these holes, but passage of bigger molecules like solute is hindered. Membranes having this kind of property are known as semi-permeable membrane. Thus, that only solvent molecule can pass through these semi-permeable membranes. If this membrane is replaced between solvent and solution as shown in figure 1.9, the solvent molecule will flow through the membrane from pure solvent of solution. This process of flow of solvent is called osmosis. The flow will continue till equilibrium is attained. The flow of the solvent from its side to solution side across semi-permeable membrane can be stopped if some extra pressure is applied on the solution. This pressure that is just stopped the flow of solvent is called osmotic pressure of the solution. The flow of solvents from dilute solution to concentrated solution across semi-permeable membrane is due to osmosis. The important point to keep in mind is that solvent molecules always flow from lower concentration to higher concentration of solution. The osmotic pressure has been found depends on concentration of solution. Figure 1.10, the excess pressure equal to the osmotic pressure must be applied on the solution side to prevent osmosis. So this is solution and this is solvent. This is semi-permeable membrane. P atmospheric plus phi is equal to, and this is P atmospheric. Osmotic pressure of solution is the excess pressure that must be applied to solution to prevent osmosis. that is to stop the pa- passage of solvent molecule through a semi-permeable membrane into solution. This is illustrated in figure 1.10. Osmotic pressure is a colligative property and it's depend on number of solute molecule and not on the identity. For dilute solution, it has been found experimentally that osmotic pressure is proportional to a molarity. C of the solution is given at temperature T. Thus, pi is equal to CRT. Here, pi is osmotic pressure and R is gas constant. Pi is equal to N2 by V into RT. Here, V is volume of solution in liter containing N2 mole of solute. If W2 gram of solute, the molar mass M2 is present in solution, then N2 is equal to W2 by M2, and we can write pi into V is equal to W2 RT by M2. M2 is equal to W2 RT by pi V. Thus, knowing the quantity W2 T and pi and V, we can calculate the molar mass of solute. Measurement of osmotic pressure provides another method of determining molar masses of solutes. This method is widely used to determine molar masses of protein, polymers, and other macromolecules. The osmotic pressure method has the advantage over other method as pressure measurement is around the room temperature and molarity of solution is used instead of molarity. Is compared to other colligative properties, its magnitude is large even for very dilute solution. The techniques of osmotic pressure for determination of molar mass of solute is particularly useful for 5 molecules as they are generally not stable at higher temperatures and polymers have poor solubility. Two solutions having same osmotic pressure at a given temperature are called isotonic solution. When such solutions are separated by semi-permeable membrane, no osmosis occur between them. For example, the osmotic pressure associated with fluid inside the blood cell is equivalent to that of 0.9% volume mass by volume sodium chloride solution called normal saline solution, and it is safe to inject intravenously. On the other hand, if we place a cell solution containing more than 0.9% mass by volume sodium chloride, water will flow out of the cell, they would shrink. Such solution is called hypertonic. If the salt concentration is less than 0.9% mass by volume, the solution is said to be a hypotonic solution. In this case, the water will flow into the cell. If placed in the solution, they would swell. The phenomena mentioned beginning of this section can be explained on the basis of osmosis. A raw mango placed in concentrated salt solution loses water by the way osmosis and shriveled into pickles. Wilted flowers revive when placed in fresh water. A carrot has become limp because water loss into the atmosphere can be placed into the water, making it form once again. Water once move into cells through osmosis. When placed in water containing less than 0.9% mass by volume salt, water cells swell due to flow of water in them by osmosis. People taking a lot of salt or salty food experience water retention in tissue cell and intracellular space because of osmosis. The resulting puffiness of swelling is called edema. Water movement from soil into plant root and subsequently into upper portion of plant is partially due to osmosis. The preservation of meat by salting of fruit by adding sugar protects against bacterial action. Through the process of osmosis, a bacterium on salted meat or candied fruit loses water, shrivels and die. Figure 1.6.5 reverse osmosis and water purification. The direction of osmosis can be reversed if pressure larger than the osmotic pressure is applied to the solution side. That is, now the pure solvent flows out the solution through semi-permeable membrane. This phenomena is called reverse osmosis and is of great practical utility. Reverse osmosis is used in desalination of seawater, a schematic setup of process shown in figure 1.11. When pressure more than the osmotic pressure is applied, water is squeezed out seawater through the membrane. A variety of polymer membranes are available for this purpose. The pressure required for the reverse osmosis is quite high. A workable porous membrane is a film of cellulose acetate placed over a suitable support. Cellulose acetate is permeable to water but impermeable to impurities and iron present in seawater. These days many countries use desalination plant to meet their potable water requirement. Figure 1.11 reverse osmosis occurs when a pressure larger than osmotic pressure is applied to solution. Water output, this is semi-permeable membrane. Here is fresh water and here is salt water. Pressure greater than osmotic pressure and here it is piston. Abnormal molar mass. We know that ionic compound when dissolved in water dissociate into cation and anion. For example, if you dissolve 1 mole of KCl in water, we expect 1 mole of potassium ion chloride ion to be released in the solution. If this happens, there would be 2 moles of particles in the solution. If we ignore inter-ionic attraction, the 1 mole of KCl in 1 kg of water would be expected to increase the boiling point by 2 into 0.52 Kelvin is equal to 1.04 Kelvin. Now if we did not know about the degree of dissociation, we could lead to conclude that mass 2 mole particles is 74.5 gram and the mass of 1 mole of KCl would be 37.25 gram. This brings into the light the rule that when there is dissociation of solid into ions, the experimentally determined molar mass is also lower than its true value. Molecules of ethanoic acid, acetic acid dimerize in benzene due to hydrogen bonding. This normally happens in solvent low electric dye constant. In this case, the number of particles is reduced due to dimerization. Association of molecule is depicted as follows. It can be undoubtedly stated here that if all molecules of ethanoic acid associated in benzene, then delta Tb and delta Tf for ethanoic acid will be half of the normal value. The molar mass is calculated on the basis of delta Tb and delta Tf will therefore be twice the expected value. Such a molar mass that is either lower or higher than the expected normal value is called as abnormal molar mass. In 8080, One-Top introduced a factor I, known as One-Top factor, to account for extent of dissociation or association. This factor is known as I is equal to normal molar mass by abnormal molar mass, or observed colligative property by calculated colligative properties. I is equal to total number of moles of particles after association or dissociation by total number of moles of particles before association or dissociation. Here abnormal molar mass is experimentally determined molar mass and calculated colligative properties are obtained by assuming that the non-volatile solute is neither associated nor dissociated. In case of association, value of I is less than the unity, while the dissociation it is greater than unity. For example, the value of I for aqueous KCl solution is close to 2, while the value of ethanoic acid in benzene is nearly 0.5. Inclusion of One-Top factor modifies the equation of colligative properties as follows. Relative lowering of vapor pressure of solvent P1 naught minus P1 by P1 naught is equal to I into N2 by N1. This is One-Top factor. Elevation of boiling point delta Tv is equal to One-Top factor into Kv into M. Depression of boiling point delta Tf is equal to I Kf into small m. Osmotic pressure of solution pi is equal to I into RT by V. Table 1.4 depicts the values of factor I for several strong electrolyte KCl, NaCl, SO4. I value approximate 2 as a solution become very dilute. As expected in solution, I get closer to 3 for K2SO4. Values of I went off factor for complete dissociation. So NaCl 2, KCl 2, MgSO4 2, and K2SO4 3. Summary: a solution of homogeneous mixture of two or more substances. Solutions are classified as solid, liquid, and gaseous solution. The concentration of solution is expressed in terms of mole fraction, molarity, molality, and its percentage. The dissolution of gas in liquid governed by Henry law, according to which at a given temperature the solubility of gas in a liquid is directly proportional to the partial pressure of gas. The vapor pressure of solvent is lowered by presence of non-volatile solute in solution. This lowering of vapor pressure of solvent is governed by Raoult's law, according to which the relative lowering of vapor pressure of solvent over solution is equal to 1 mole of fraction and non-volatile solute present in the solution. However, the binary liquid solution, if both the components of solution are volatile, then another form Raoult's law is used. Mathematically, this form of Raoult's law is stated as P total is equal to P1 not x1 plus P2 x2 P2 not x2. Solutions which obey Raoult's law over the entire range of concentration are called ideal solution. Two types of deviation from Raoult's law called positive deviation and negative deviation observed. Azeotrophs arise due to very large deviation from Raoult's law. The properties of solution which depend upon the number of solute particles are independent on their chemical identity called colligative properties. These are lowering in vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. The process of osmosis can be reversed if a pressure higher than the osmotic pressure is applied to the solution. Colligative properties have used to determine molar mass of solutes. Solutes which dissociate in solution exhibit molar mass lower than the actual molar mass of, and those which associate show higher molar mass than their actual value. Quantitatively, the extent to which a solute dissociate or associate can be expressed by Van of factor I. This factor has been defined in ratio normal molar mass to experimental determined molar mass or in ratio of observed colligative properties to the calculated properties. So, solution NCRT reading completed. Unit 2 electrochemistry. This will 40 m. मिलते हैं भाई ब्रेक के बाद, 5 मिनट का ब्रेक, उसके बाद करते हैं इलेक्ट्रोकेमिस्ट्री. मेरी जाना क्यों नहीं जाना दर्द मेरा आशिक तेरा। यूं भीड़ में खोया रहता हूँ। हो गया भाई, ब्रेक कंप्लीटेड. सो we are going to start electrochemistry. आशिक तेरा यूं भीड़ में खोया रहता है जाने जहाँ. Chapter 2, Electrochemistry. Chemical reaction can be used to produce electrical energy. Conversely, electrical energy can be used to carry out chemical reactions that do not proceed spontaneously. Electrochemistry is the study of production of electricity from energy released during spontaneous chemical reaction. Sorry. And the use of electrical energy to bring about non-spontaneous chemical transformations. The subject of importance both for theoretical and practical consideration. A large number of metals, sodium hydroxide, chlorine, fluorine, and many other chemicals produced by electrochemical methods. Batteries and fuel cells convert chemical energy into electrical energy and are used on a large scale in various instruments and devices. The reaction carried out electrochemically can be energy efficient and less polluting. Therefore, study of electrochemistry is important for creating new technologies that are eco-friendly. The transmission of sensory signal through cells to brain and vice versa, and communication between the cells are known to have electrochemical origin. Electrochemistry is therefore a very vast and interdisciplinary subject. In this unit, we will cover only some of the important elementary aspects. Electrochemical cell. We had studied construction of function of Daniell cell. This cell converts chemical energy liberated during the redox reaction. Zinc solid react with copper ion, aqueous form zinc ion plus copper in electrical energy and has an electrical potential equal to 1.1 volt. When concentration of zinc and copper ion is unity 1 molar per decameter cube, such a device is called galvanic or a voltaic cell. If external opposite potential is applied to galvanic cell and increase slowly, we find that reaction continues to take place till the opposing voltage reaches the value 1.1 volt. When the reaction stops altogether and no current flows through the cell, any further increase in the external potential again start the reaction but in the opposite direction. It's now function as an electrolytic cell, a device for using electrical energy to carry non-spontaneous chemical reactions. Both types of cells are quite important and we shall study some of their salient features in the following pages. Figure 2.1, Daniell cell having electrode of zinc and copper dipping in solution of their respective salts. Solution containing salt of zinc, solution containing salt of copper. This is salt base and this is zinc, this is copper, and current flow from copper to zinc rod and electron flow from zinc to copper rod. 2.2, functioning of Daniell cell when external voltage E external opposing the cell potential is applied. First, when external potential is less than 1.1 volt, then first electron flow from zinc to rod to copper rod, hence current flow from copper rod to zinc rod. Second, zinc dissolve at anode and copper deposited cathode. When external E external is equal to 1.1 volt, no flow of electron or current, no chemical reaction. C, when external voltage is greater than 1.1 volt, electron flow from copper to zinc and current flow from zinc to copper. Second, zinc is deposited at zinc electrode and copper is dissolved at copper electrode. 2.2 Galvanic cell. As mentioned earlier, a galvanic cell is an electrochemical cell that converts the chemical energy of a spontaneous redox reaction into chemical energy. In this device, the Gibbs energy of the spontaneous redox reaction is converted into electrical work, which may be used for running a motor or other electrical gadget like heater, fans, geyser, etc. Daniel cell discussed earlier in one such cell in which following redox reaction occur. Zinc solid reacts with copper ion to form zinc ion plus copper solid. This reaction is combination of two half cell reaction whose addition gives to overall cell reaction. Copper ion react with 2 electron from copper solid and zinc solid gives 2 electron to form zinc ion. This is reduction half reaction and this is oxidation half reaction. These reactions occur in two different portions of Daniel cell. The reduction half reaction occur on the copper electrode while the oxidation half reaction occur on the zinc electrode. These two portions of the cell are also called half cell or redox couple. The copper electrode may be called reduction half cell or zinc electrode the oxidation half cell. We can construct innumerable number of galvanic cell on the pattern of Daniel cell by taking combination of different half cells. Each half cell consists of metallic electrode dipped into the electrolyte. The two half cells are connected by metallic wire through a voltmeter and a switch externally. The electrolyte of the two half cells are connected internally through salt bridge as shown in figure 2.1. Sometimes both the electrode dip in the same electrolyte solution. In such cases, we do not require salt bridge. At each electrolyte interface, there is tendency of metal ion from solution to deposit on the metal electrode trying to make it positively charged. At the same time, metal atom of the electrode have a tendency to go into the solution as ions and leave behind the electrons at the electrode trying to make it negatively charged. At equilibrium, there is separation of charges and depending on the tendency of two opposing reactions, the electrode may be positively or negatively charged with respect to solution. A potential difference develops between the electrode and electrolyte which is called electrode potential. When the concentration of all the species involved in a half cell unity, then electrode potential is known as standard electrode potential. According to IUPAC convention, standard reduction potential are now called standard electrode potential. In a galvanic cell, the half cell in which oxidation takes place is called anode and it has a negative potential with respect to the solution. The other half cell in which reduction takes place is called cathode and it has a positive potential with respect to solution. Thus, there exists a potential difference between the two electrodes. As soon as the switch is in the on position, the electrons flow from negative electrode to positive electrode. The direction of current flow opposite to the direction of electron flow. The potential difference between two electrodes of galvanic cell is called cell potential and is measured in volts. The cell potential of difference between the electrode potential reduction potential of the cathode and anode. It is called cell electromotive force EMF of the cell when no current is drawn through the cell. It is now accepted convention that we keep the anode on the left and the cathode on the right while representing the galvanic cell. A galvanic cell is generally represented by putting vertical line between metal and electrolyte solution and putting double vertical line between two electrolytes connected by salt bridge. Under this convention, the EMF of cell positive uh, and is given by a potential half cell on the right hand side minus the potential half cell on the left hand side. That is, E cell is equal to E right minus E left. This is illustrated by the following example. Cell reaction copper solid plus 2Ag plus aqueous form copper 2 plus aqueous plus 2Ag solid. Half cell reaction cathode at cathode reduction occur. 2Ag plus form Ag solid and at anode oxidation occur. Copper form copper ion. It can be seen that sum of 3.5 and 3.6 led to overall reaction 2.4. In the cell, that silver electrode acts as cathode and copper electrode acts as anode. This cell can be represented as copper solid plus copper ion. It form copper ion and Ag plus form Ag plus. And we have E cell is equal to E right minus E left, or E Ag plus E cathode minus E anode. The potential of the individual half cell cannot be measured. Measurement of electrode potential. The potential of electrode half cell cannot be measured. We can measure only the difference between the two half cell potential that give the EMF of the cell. If we arbitrarily choose the potential of one of electrode half cell, then that of other can be determined with respect to this. According to convention, a half cell called standard hydrogen electrode represented by platinum solid H2 gas form H plus aqueous. It assigned a zero potential at all temperature corresponding to the reaction. H plus electron form half H2. The standard hydrogen electrode consists of platinum electrode coated with platinum black. The electrode is dipped in an acidic solution and pure hydrogen gas is bubbled through it. The concentration of both the reduced and oxidized form of hydrogen is maintained at unity, figure 2.3. This implies that the pressure of hydrogen gas is 1 bar and the concentration of hydrogen ion is in solution is 1 molar. Figure 2.3, standard hydrogen electrode finely divided platinum coated with platinum foil, 1 molar H plus ion H2 gas at 1 bar pressure. At 298 Kelvin, the EMF of cell standard hydrogen electrode, second half cell constructed by taking standard hydrogen electrode as anode, reference half cell, and the other half cell is as cathode, gives the reduction potential of the other half cell. If the concentration of oxidized and reduced forms of species right hand half cells are unity, the cell potential is equal to standard electrode potential E naught R of the given half cell. E naught is equal to E naught R minus E naught I. As E naught L of the left of standard hydrogen electrode is 0, E naught is equal to E naught right minus 0 is equal to E naught R. The measured EMF value of cell is platinum solid H2 at 1 bar plus aqueous and copper 2 plus aqueous is form copper is 0.34 volt, and it is also value of standard electrode potential of the half cell corresponding to reaction copper 2 plus aqueous formed with the plus 2 electron form copper solid. Similarly, measured EMF of cell is this is 0.76 volt corresponding to the standard electrode potential of half cell. The positive value of standard electrode potential in the first case indicated that copper plus 2 ion get reduced more easily than hydrogen ion. Then reverse process cannot occur, that is, hydrogen ion cannot oxidize copper, or alternatively we can say that hydrogen gas can reduce copper ion. Under the standard condition described above, the copper does not dissolve in HCl. The In nitric acid, it is oxidized to nitrate ion and not by hydrogen ion. The negative value of standard electrode potential in second case indicate that hydrogen ion can oxidize zinc or zinc can reduce hydrogen ion. In view of the convention, the half reaction of the Daniell cell in figure 2.1 can be written as left electrode zinc form zinc ion aqueous 1 molar plus 2 electron, and right electrode copper 2 plus form copper solid. The overall reaction of cell is the sum of above two reactions we obtain as zinc plus copper ion form zinc ion plus copper solid. EMF of the cell is equal to E naught cell is equal to E naught right minus E naught left is equal to your E naught cathode minus E naught anode is equal to 0.34 volt minus 0.76 is equal to 1.10 volt. Sometimes metal like platinum or gold used as inert electrode. They do not participate in the reaction but provide their surface for oxidation reaction and for conduction of electrons. For example, platinum is used in the following half reaction: hydrogen electrode platinum solid H2 H plus with half cell reaction H plus aqueous plus electron half H2, bromine electron PT Br2 Br minus aqueous with half cell reaction half Br2 aqueous plus electron Br minus aqueous. The standard electrode potential are very important and we can extract a lot of useful information from them. The values of standard electrode potential for some selected half cell reduction reaction are given in table 2.1. If the standard electrode potential of an electrode is greater than that of 0, then the reduction half is more stable than compared to hydrogen gas. Similarly, if the standard electrode potential is negative, then hydrogen gas is more stable than the reduced form of the species. It can be seen that standard electrode potential for fluorine is the highest in the table, indicating that fluorine F2 gas has the maximum tendency to reduce the fluoride ion F minus, and therefore fluorine gas is the strongest oxidizing agent and fluoride ion is the weakest reducing agent. Lithium has the lowest electrode potential, indicating that lithium ion is the weakest oxidizing agent, while lithium metal is most powerful reducing agent in an aqueous solution. It may be seen that as we go from top to bottom in table 2.1, the standard electrode potential decreases, and with this decrease in oxidizing power of species on left and increases reducing power of the species on the right hand side of reaction. Electrochemical cells are extensively used for determining pH of solution, solubility, product, equilibrium constant, and other thermodynamic properties for potentiometer titration. 2.3 Nernst equation. We have assumed that the previous section that the concentration of all species involved electrode reaction is unity. This need not be always true. Nernst equation show that the electrode potential reaction Mn plus in aqueous plus an electron form M solid. The electrode potential at any concentration measured with respect to standard hydrogen electrode can be represented by Mn plus form M metal is equal to E naught M to the power N plus M minus RT by NF ln M by Mn plus. But concentration of solid M is taken as unity, and we have E Mn plus by Mn is equal to E naught Mn plus by Mn minus RT by NF ln 1 by Mn to the power N plus. E naught Mn plus form Mn has already defined. R is gas constant 8.314 joule per Kelvin per mole. F is Faraday constant 96,487 coulomb per mole. T is temperature in Kelvin, and M plus is concentration of species Mn plus. Standard electrode potential at 298 Kelvin. Ions represent the aqueous solution and H2 as liquid gases and solid as shown in by G and S. Electron per volt reduced for reaction of oxidized form of plus Na. This is E naught V. Increasing strength of reducing agents, and this is increasing strength of oxidizing agent. So F2 is most oxidizing and Li plus is most reducing. A negative E naught means the redox couple is weaker strong reducing agent than H plus or H2 couple. A positive E naught means that the redox couple is weaker reducing agent than H plus or H2 couple. A Daniell cell, the electrode potential of any given concentration Cu plus and Zn plus 2 ions are written as for cathode E copper form Cu is equal to E naught Cu plus 2 by copper minus RT by 2F ln 1 by Cu plus 2 aqueous. At anode E zinc 2 plus zinc form E naught zinc 2 plus zinc minus RT by 2F ln 1 by Zn 2 plus aqueous. This cell potential E naught is equal to E cathode minus E anode. So after applying last equation, we get finally E cell is equal to E naught RT by 2F ln Zn 2 plus by copper 2 plus. It has been seen that E naught E cell depends on concentration of both copper and zinc ion. It increases with increasing concentration of copper ion and decreases with concentration of zinc ion. By converting the natural logarithm 2.10 to the base 10 and substituting R value, we get at t is equal to 29. It reduced to E cell is equal to E naught 1 E naught minus 0.59 by 2 log Zn 2 plus by copper 2 plus. We should use same number of electrons N for both electrode, and thus following reaction nickel solid form nickel 2 plus aqueous and Ag plus 2 form Ag. This cell reaction of nickel solid plus 2Ag plus is equal to Ni aqueous plus 2Ag. The next equation can be written as E cell is equal to E naught cell minus RT by 2F ln Ni2 plus by Ag2 plus. And for general electrochemical reaction of this reaction, A plus BB for in the presence of an electron form Cc plus Dd. Next equation can be written as E is equal to E naught cell minus RT by NF ln Q. E naught cell is equal to minus NF ln C to power C by D power D by A to power A B power B. 2.3.1 equilibrium constant from next equation. If the circuit in Daniell diagram is closed, then we note that the following reaction: zinc plus 2 copper aqueous form zinc 2 plus aqueous plus copper solid. Take place as time passes. The concentration of zinc 2 plus keeps on increasing, while the concentration of Cu2 plus on decreasing. At the same time, voltage of the cell as read on the voltmeter keeps on decreasing. After some time, we shall note that there is a change in the concentration of copper 2 plus and zinc 2 plus ion, and at the same time voltmeter gives 0 reading, this indicating that experiment equilibrium has been attained. In this situation, E naught equation may be written as E naught is equal to 2.303 RT by 2F log Zn 2 plus by Cu2 plus, where the equilibrium Zn 2 plus by Cu2 plus is equal to Kc for the reaction 2.1. And at temperature T is equal to 298 Kelvin, the above equation can be written as E naught cell is equal to 0.059 V by 2 log Kc is equal to 1.1 V log Kc is equal to 1.1 V into 2 by 0.059 is equal to 37.288. In general, E naught cell is equal to 2.303 RD by NF log Kc. Gives figure 2.14, equation 2.14 gives relationship between equilibrium constant and reaction of standard potential of cell in which that reaction take place. Thus equilibrium constant of the reaction difficult to measure, otherwise can be calculated from corresponding E naught value of the cell. Electrochemical cell and gives free energy. Electrical work in 1 second is equal to electrical potential multiplied by total charge passed. If we want to obtain maximum work from a galvanic cell, then we charge that has to be passed reversibly. The reversible work done by galvanic cell is equal to decrease in Gibbs energy, and therefore the EMF of cell is equal, and NF is the amount of charge passed, and delta G of is the Gibbs energy of the reaction. Then delta Rg is equal to minus NF cell. It may be remembered that E cell is intensive parameter, but delta Rg is extensive thermodynamically property, and its value depend on N. If the same equation written as Zn 2 plus copper, it forms Zn ion plus copper solid. Delta Gr is equal to minus NFe cell. But when we write the reaction 2 Zn solid form plus 2 copper plus aqueous form zinc ion plus copper solid. Delta G is equal to minus 4 Rfe. If the concentration of all reacting species unity, then E cell is equal to E naught cell, and we have delta G naught is equal to NF E naught. Thus the measurement of E naught cell we can obtain an important thermodynamically quantity. Delta G R naught standard gives energy of the reaction. From later we can calculate equilibrium constant of the equation. Delta Rg naught is equal to minus RT ln K. Conductance of electrolytic solution. It is necessary to define a few terms before we consider the subject of conductance of electricity through electrolytic solution. The electrical resistance is represented by symbol R, and it is measured in ohm, which is termed as SI base unit is equal to kg per meter, kg meter square per SQA square. It can be measured with help of Wheatstone bridge, with which you familiar from your study of physics. The electrical resistance of any object directly proportional to its length L and inversely proportional to area of cross section A from it, that is R directly proportional to L by A. R is equal to rho L by A. The constant proportionality rho, Greek rho, is called resistivity specific resistance. Its SI unit are ohm meter, and quite often it's some multiple ohm centimeter in case also. IPSC recommends the use of long-term resistivity over specific resistance. Hence, in the rest of the book we shall use the term resistivity. Physically, the resistivity of for substance is in negative, and when it 1 meter long and its area of cross section is 1 meter square, it can be seen that 1 ohm meter is equal to 100 ohm centimeter, or 1 ohm centimeter is equal to 0.01 ohm meter. The inverse resistance R is called conductance. G is when the relation G is equal to 1 by R is equal to A by rho L is equal to K A by L. The SI unit of conduction of Siemens says by the symbol as and equal to volume, also known as mho or ohm. The inverse of resistivity called conductivity. Specific conductance is represented by symbol K. The IPC has recommended the use of term conductivity over specific conductance. The SI unit conductivity is Simon per meter, but quite often K is expressed as Simon per centimeter. The conductivity of material Simon per meter is conductance when it is 1 meter long and its area is cross section is 1 meter square. It may be noted as 1 Simon per centimeter is equal to 100 Simon per meter. Table 2.2, the value of conductivity of some related species 2.85. It can be seen in table 2.2 that magnitude of conductivity varies in different great deal. Depends on the nature of material. It also depends on the temperature and pressure at which the measurements are made. Materials are classified into conductor, insulator, and semiconductor depending on magnitude of their conductivity. Metals and their alloy have been very large conductivity and are also known as conductors. Certain non-metals like carbon, atom, graphite, and some organic polymers are also into electronically conducting. Substances like glass, ceramics, etc., having very low conductivity are known as insulators. Substances like silicon, doped with silicon and gallium arsenide, having conductivity between conductors are milestone and are called semiconductors as import electrons material. Certain material called superconductor by definition of have zero resistivity or infinite conductivity. Earlier zero computer earlier only metal and alloy are very low temperature 0 to 50 Kelvin when known to have behave as superconductor, but nowadays a number of ceramic material mixed oxide are also used to show superconductivity temperature at 150 Kelvin. Electrical conductance through metal and metallic or electronic conduction is due to the movement of electron. The electron conductance depends on first nature of state nature and structure of metal, second number and valence electron per atom, third temperature and its decrease and its increased temperature. A electron ether and one of go through other ends. The composition of metallic conductor remain unchanged. The mechanism conductor through semiconductor is more complex. We already know that even very pure water has a small amount of hydrogen and destroy, which led to very low conductivity. When electrolyte is dissolved in water, they furnishes their own solution and its conductivity also increases. The conductance of electricity by Pw in this solution is called ionic conductance. The conductivity of electrolyte ionic solution depends on nature of electrolytes, size of ion produced and their solution. Third, the nature of solvent and its viscosity. Fourth, concentration of electrolyte. Fifth, temperature of temperature it increase with increasing temperature. Passive direct current through ionic solution over prolonged period can lead to change in composition due to electrochemical reaction. 4.2.1 Measurement of conductivity of ionic solution. We know that accurate measurement of unknown solution can be performed with a stone bridge. However, the measuring of resistance of an ionic solution face two problems. Firstly, passing direct ion DC changes of composition in solution. Secondly, a solution cannot be connected to salt bridge like a metallic wire and other solid conductor. The first difficulty in resolving using an alternating AC current source of power. The second problem is solved by using a specially designed vessel called conductivity cell. It is available for several designs and use simple molecule shown over. Two different type of conductivity cell: platelized electrode, platinum electrode wires. These are connecting wires, and this is platinum electrode. Basically, it consists of two platinum electrode coated with platinum. Black finely divided metallic platinum is projected on electrode electrochemically. These have area cross section equal to A and are separated at distance L. Therefore, solution confined between these electrons in column of length L and area of cross section A. The resistance of such column of solution is given by R is equal to rho L by A, L K by A. The solution L by A is called cell constant, denote the symbol G naught, G dash. It depends on the distance between electrode and their area of cross section has dimension of length per length and can be calculated if we have L and A. Measurement of L and A not only inconvenience but are unreliable. This cell constant is usually determined by measuring the resistance of cell containing a solution of which conductivity is already known. For this purpose, they generally use KCl solution whose conductivity is also known as accurately various concentration. And at different temperature, the cell constant G naught is then given by the equation G naught is equal to L by is equal to RK. Conductivity of molar conductive KCl at 298 Kelvin. Arrangement and measurement of an resistance of an electrolyte. Conductivity of cell, this is detector. Once a cell constant is determined, we can use it for measuring resistance and conductivity of a solution. The setup on measurement of resistance given 2.5. It is consists of two resistors R3 and R4, a variable resistance R1 and conductivity cell having unknown resistance R2. The resistance is fed by an oscillator O source AC power audio frequency range 500 to 50 to 5000 cycle per second. P is suitable detector or a headphone or other electronic device, and a bridge balanced when no current passes through the detector under this condition. Unknown resistance R2 is equal to R1 R4 by R3. These days, inexpensive conductivity meter are available which can directly read conductance or resistance of the solution in conductivity cell. Once the cell constant and resistance of solution cell is determined, the conductivity of solution is given as K is equal to cell constant by R. The conductivity of solution is different electrolyte in same solvent at given temperature differ due to the charge and size of the ions which they dissociate. The concentration of ions or each which ion move under the is potential content is therefore become necessary to define physically more meaningful quantity called molar conductivity, denoted by symbol lambda m. It is related to conductivity of solution by equation molar conductivity is equal to K by C. In the above equation, K is expressed as Simon per meter and concentration C mole per meter cube. Then the unit of lambda m are Simon per meter cube per mole. It may be noted that 1 mole per meter cube is equal to 1000 liter per meter cube into molarity mole per liter, and hence lambda m is equal to K by 1000 liter per meter cube into molarity. If we use Simon per centimeter as unit of kappa and mole per centimeter cube the unit of concentration, then the unit of lambda m is equal to Simon centimeter square per mole. It can be calculated by using equation lambda m is equal to K into 1000 centimeter cube by molarity mole per liter. Both type of unit usually in literature are related to as 1 Simon meter square per mole is equal to 10 to the power 4 Simon per centimeter per mole, or 1 Simon per centimeter per mole is equal to 10 to the power minus 4 meter square per mole. Variation of conductivity or molar conductivity of with concentration. Both conductivity and molar conductivity change with the concentration of electrolyte. Conductivity always decreases with decreasing concentration both for weak and strong electrolyte. This can be explained by the fact that the number of ions per unit volume that carry the current in solution decreases on dilution. The conductivity of solution at any given concentration is the conductance of 1 unit volume of solution kept to platinum electrode with area of cross section at distance unit length. This is clear from the reaction G is equal to K by L. K, both A and L is unity and that operate at unit m and m centimeter. Molar conductivity of a solution is given at a given concentration in a conductance. The volume V of a solution containing 1 mole of a electrolyte kept between two electrodes of area of cross section A and distance of unit length. Therefore, lambda m is equal to K by L is equal to kappa. Since L is equal to 1 and A is equal to V, volume containing 1 mole of electrolyte, lambda m is equal to K into V. Molar conductivity versus 1 by under root C for acetic acid, weak electrolyte, and this is strong electrolyte. Molar conductivity increases with decrease in the concentration. This is because the total volume V of solution containing 1 mole of electrolyte also increases. It has been found that decrease in K conductivity on a solution of a conductivity on a solution of a on dilution of a solution is more than compensated by increase in its volume. Physically, it means that at a given concentration, lambda m can be defined as a conductance of electrolytic solution kept between electrodes of a conductivity cell at a unit distance between, having area of cross section large enough to accommodate sufficient volume of solution that contains 1 mole of the electrolyte. When concentration approaches 0, the molar conductivity is also known as limiting molar conductivity and is represented by lambda m naught. The variation of lambda m with concentration is different for strong electrolyte. For strong electrolyte, the electrolyte lambda m increases with slowly dilution and can be represented as lambda is equal to lambda naught minus a under root c. It can be seen that if we plot lambda m against under root c, we obtain a straight line with intercept equal to lambda m and slope equal to minus a. The value of constant A is given to solvent and temperature depends on the type of electrolyte, that is, charges on the cation and anion produces dissociation of electrolyte in the solution. Thus, NaCl and calcium chloride, magnesium sulfate are also known as 1:1, 2:1 or 2:2 electrolytes respectively. All electrolyte particularly type have the same value of for A. Kohlraasch examined lambda m value for a number of strong electrolyte, observed certain irregularities. He noted that difference in lambda m naught for electrolyte NaX and Kx for NEX nearly constant for molecule. Lambda m KCl is equal to lambda m KCl minus lambda m NaCl is equal to lambda m KVr minus lambda m NVr. Similarly, it was also found as lambda NVr minus lambda m NaCl, lambda naught m KVr minus lambda m KCl, 1.8 Simon centimeter square per mole. On the basis of above observation, he enunciated Kohlraasch's law of independent migration of ion. The law stated that limiting molar conductivity of an electrolyte can be represented as sum of the individual contribution of anion and cation of the electrolyte. Thus, if lambda sodium ion or lambda chloride ion are limiting molar conductivity of sodium and chloride ions respectively, then limiting molar conductivity of sodium chloride given lambda NaCl lambda naught plus Na plus lambda chloride ion In general, if electrolyte dissociated to give V plus cation and V minus anions, then its limiting molar conductivity is given as lambda m is equal to V lambda naught V lambda naught. Here lambda naught plus and lambda naught minus are limiting molar conductivity of cation and anion. Respective values of lambda naught for cation and anion are given in table 2.4. Weak electrolytes. Weak electrolytes of acetic acid have lower degree of dissociation at higher concentration. Hence, such electrolyte, the change in lambda m dilution is due to increase in degree of dissociation, and consequently the large number of ion total volume of solution that contain 1 mole of electrolyte. In such cases, lambda m increases steeply on dilution, especially near lower concentration. Therefore, lambda m cannot be obtained by extrapolation of lambda m to zero concentration. At infinite dilution, that is concentration C to 0, electrolyte dissociate completely. Lambda alpha is equal to 1, but at the same temperature concentration, the conductivity of solution is so low that it cannot be measured accurately. Therefore, lambda m naught for weak electrolyte is obtained by using Kohlrausch law, independent migration of ion. At any concentration of C, if alpha is degree of dissociation, then it can be approximately to ratio of molar conductivity lambda m at the concentration C of limiting molar conductivity lambda m. Thus, alpha is equal to lambda m by lambda m naught. K is equal to C alpha square by 1 minus alpha. Application of Kohlrausch law. Using Kohlrausch law of independent migration of ion, it is possible to calculate lambda m naught for any electron from lambda m naught individual ion. Moreover, for weak electrolyte like acetic acid, it is possible to determine the value of dissociation constant once we know lambda m naught and lambda m at given concentration C. Electrolytic cell or electrolysis. In electrolytic cell, external source of voltage is used to bring about a chemical reaction. The electrochemical process are of great importance in laboratory and chemical industry. One of the simplest electrolytic cell consists of two copper strip dipping in aqueous solution of the copper sulfate. In DC voltage is applied to two electrodes, then copper ion discharge at cathode negatively charged and follow the reaction copper plus 2 aqueous in presence of two electrons from copper solid. Copper metal is deposited on cathode. At the anode, copper is converted to Cu2 plus ion by reaction copper solid copper 2 plus 2 electron. Thus the copper is dissolved in oxidized at anode and deposited reduced at cathode. This is the basic of for all industry process in which impure copper is converted into copper of high purity. The impure copper is made an anode that dissolves on passing current, and pure copper is deposited at cathode. Many metals like sodium, magnesium, aluminum, etc. are produced on large scale by electrochemical reduction of their respective cation, where no suitable chemical reducing agent available for this purpose. Sodium magnesium metal produced by electrolysis of fused chloride, and aluminum is produced by electrolysis of sodium oxide presence of cryolite. Quantitative aspect of electrolysis. Michael Faraday was first scientist who described quantitative aspect of electrolysis. Now, Faraday laws also follow that from what has been discussed in earlier. Faraday law of electrolysis. After an extensive investigation of electrolysis solution and melt electrolytes, Faraday published his result during 1834 in the form of following known Faraday two laws of electrolysis. First law: the amount of chemical reaction which occur at any electrode during electrolysis by a current is proportional to the quantitative electricity passed through electrolyte solution or melts. Second law: the amount of different substances liberated by the Same quantity of electricity passes through electrolytic solution are proportional to their chemical equivalent weight, atomic mass of metal divided by number of electrons required to reduce the cations. There are no constant current sources available during Faraday times. The general practice was to put coulometer, a standard electrolytic cell for determining the quantity of electricity passed through from the amount of metal, generally silver or copper, deposited or consumed. However, coulometers are now obsolete and we now have constant current I source available, and the quantity of electricity Q passed is given by Q is equal to IT. Q is in coulomb when I is ampere, T is in second. The amount of electricity or charge required for oxidation of or reduction depends on the stoichiometry of electrode reaction. For example, Ag plus aqueous plus electron form Ag solid. 1 mole of electron is required for reduction of 1 mole of silver ion. We know that 1 electron is equal to 1.6 into 10 minus 90 coulomb. Therefore, the charge on 1 mole of electron is 96,487 coulomb per mole. This quantity is known as Faraday and is represented F. Thus, approximate calculation we use 1 Faraday is equal to 96,500 coulomb per mole. For electron potential, Mg plus 2 electron for Mg solid and Mg 3 plus 3 electron for aluminum. It is observed that 1 mole of Mg2 plus and aluminum 3 plus require 2 mole of electron 2f and 3 mole of electron 3f respectively. The charge passed through electrolytic cell during electrolysis is equal to the product of current and ampere and time in second. In commercial production of metal, current is high 50,000 ampere and used that amount to about 0.518 Faraday per second. 2.51 product of electrolysis. Product of electrolysis depend on the nature of material being electrolyzed and type of electrode being used. If the electrode is inert platinum or gold, it does not participate in chemical reaction and acts only as a source of sink for electrons. On the other hand, if the electrode is reactive, it participate in electrode reaction. Thus, product of electrolysis may be different from reactive of inert electrode. The product of electrolysis depend on different oxidizing reducing species present in electrolytic cell and their standard electrode potential. Moreover, some of electrochemical processes, although feasible, are so slow kinetically that at lower voltage these not seem to take place, and extra potential called over potential has to be applied, which makes such process more difficult to occur. For example, if we use molten NaCl, the product of electrolysis are sodium metal Cl2 gas. Here we have only one cation Na plus, which is reduced to cathode Na plus plus electron Na, and one cation Cl minus, which is oxidized at anode. During electrolysis of aqueous sodium chloride solution, the product are NaOH, chloride gas, and chlorine gas and hydrogen gas. In this case, Na plus and Cl minus ion, also H plus and OH minus ion, along with solvent molecule H2O. At the cathode, there is competition between following reaction: sodium for solid, hydrogen for hydrogen. The reaction is higher E0 value preferred, and therefore the reaction of cathode during electrolysis is S plus plus 2 electron form H2 gas, but S plus produced by dissociation of H2 is H2O liquid S plus aqueous plus OH minus aqueous. Therefore, the net reaction of cathode may be written as the sum of 2.34 and 2.34 H2 plus electron form half H2 gas plus OH minus. The electron potential reaction is follows: chloride and aqueous form half chlorine gas plus electron, H2O liquid form O2 plus 4 OH plus 4 electron. The reaction at anode with lower value of E naught prepared, and therefore water should get oxidized and preference of 2 chloride ion. However, on account of over potential oxygen reaction 2.36 is preferred. Thus, net reaction may be summarized as NaCl cathode and this NaCl and anode reaction. The standard potential are reference electron potential given by Nernst equation 2.8 take into account of concentration effect. During electrolysis of sulfuric acid, the following process are possible as anode H2O form H2 plus 4OH plus 4 electron E naught cell plus 1.2.3. हैकर है भाई हैकर. H2O liquid form H2O2 gas plus 4H plus 4 electron E naught is equal to 1.23. Sulfate ion in aqueous form H2OA 2 minus plus 2 electron E naught cell 1.98. For dilute sulfuric acid reaction 2.38 preferred, but at higher concentration H2SO for reaction 2.39 is preferred. 2.6 batteries. Any battery actually it has one or more than one cell connected in series, or cell that we use once in electrical energy, basically a galvanic cell, where the chemical energy of redox reaction is converted into electrical energy. However, for a battery to be practical use, one should be reasonably light, compact, and its voltage should not be vary appreciably during its use. These are mainly two types of battery. 2.6.1 primary battery. In primary battery, the reaction occur only once, and after use of over a period of time, battery becomes dead and cannot be reused again. The most familiar example of this type of dry cell known as Leclanche cell after discovery, which is used commonly in our transistor and clocks. This cell consists of zinc container that also acts as anode and cathode as carbon graphite rod surrounded by powder magnesium dioxide carbon. The space between electrode is filled with moist paste of ammonium chloride NH4Cl and zinc chloride ZnCl2. The electrode reactions are complex, but they can be written approximately as follows: anode and a cathode. In the reaction at cathode, magnesium is reduced from plus 4 oxidation state to plus 3 state. Ammonia produced in the reaction form complex with Zn2 plus to give ZnNH3 4 plus 2 plus. The cell has a potential nearly 1.5 volt. Mercury cell suitable for low current devices like hearing aids, watches, etc. consist of zinc mercury amalgam as anode and a paste of HgO and carbon as the cathode. The electrolyte is a paste of KOH and ZnO. The electrode reaction of cell is given at anode ZnHg form ZnO plus H2 plus 2 electron and HgO form Hg plus 2OH. Commercial dry cell consists of a graphite cathode in a zinc battery and later acts as anode. This is graphite rod cathode, and this is zinc cup anode, and this is MnO2 carbon black plus NH4Cl paste. The overall reaction is represented as zinc Hg plus HgO solid bond ZnO plus Hg. The cell potential is approximately 1.35 volt and remain constant during its life, as the overall reaction does not involve any ion in solution whose concentration can change during its lifetime. Commonly used mercury cell. The reducing agent is zinc and oxidizing agent is mercury second oxide. Anode, this is anode cap, and this is cathode, this is gasket, this is separator, this is cell can. Secondary battery. A secondary cell after use can be recharged by passing current through it is opposite direction so that it can be used again. A good secondary cell can undergo a large number of discharging and charging cycles. The most important secondary cell is the lead storage battery, commonly used in automobile and inverters. It consists of lead anode and grid lead packed with lead oxide PbO2 as cathode, or 38% solution of sulfuric acid is used as electrolyte. This cell reaction when battery is used is given below. Anode PbS plus SO4 2 minus PbSO4. Cathode PbO2 plus SO4 2 minus form PbSO4 plus water. The overall reaction consisting of cathode and anode reaction is Pb solid plus PbO2 plus 2s2 H2SO4 form 2 PbSO4 plus 2H2O. On charging the battery, reaction is reversed. PbSO4 on anode and cathode converted into Pb and PbO2 respectively. This is cathode and this is anode. This is negative plates, leads grids filled with spongy lead, and this is positive plate grid filled with PbO2. (38% sulfuric acid solution) or rechargeable nickel cadmium nickel cell jelly roll arrangement and separate by a layer of soaked moist potassium, sodium and potassium hydroxide. Another important secondary cell is nickel cadmium cell, which has a longer life than the lead storage cell but more expensive to manufacture. We shall not go into detail for working of the cell of electrode reaction charging discharging. Overall reaction of discharging is cadmium plus 2 NiOH3 form cadmium oxide plus 2 NiOH whole twice plus H2O. Fuel cell. Production of electricity by thermal is not very efficient under normal under major source of pollution. In such plant, chemical energy heat combustion of fossil fuels, coal, gas, oils is first used for converting water into high pressure steam. This is then used to run a turbine to produce electricity. We know that galvanic cell directly converts chemical energy into electricity and is slightly efficient. It is now possible to make such cell in which reactants are fed continuously to the electrode and product are removed continuously from the electrolyte compartment. Galvanic cells that are designed to convert the energy combustion fuel like hydrogen, methane, methanol, etc. directly into electrical energy is called fuel cell. Fuel cell using H2 and O2 introduce electricity. O2, H2, this is anode, this is cathode, aqueous electrolyte. One of the most successful fuel cell used reaction hydrogen with oxygen to form water. This cell was used to providing electrical power in the Apollo space program. The water vapors produced during the reaction were condensed and added to the drinking water supply for astronauts. In the cell, hydrogen and oxygen are bubbled through porous carbon electrode into concentrated aqueous sodium hydroxide solution. Catalysts like finely divided platinum and palladium metal incorporated into electrode for increasing the rate of electrode reaction. The electrode reaction are as given below. Cathode O2 plus H2O 4 plus 4 electron 4 OH minus, and anode H2 plus 4 OH minus H2 plus 4 electron. Overall reaction being 2H2 gas plus O2 gas form 2H2O. The cell runs continuously as long as reactant are supplied. Fuel cell produce electricity with efficiency of about 70% compared with thermal plants whose efficiency is about 40%. There has been tremendous progress in development of new electrode material, better catalyst and electrolyte for increasing efficiency of fuel cell. These have been used for automobile and experimental phases. Fuel cells are pollution free, and view of their future importance, a variety of fuel cells have been fabricated and tried. 2.8 Corrosion. Corrosion slowly coats the surface of metallic object with oxides or other salt of metal. The rusting of iron is tarnishing of silver, development of green coating of copper and bronze are some of the examples of corrosion. It causes enormous damage to building, bridges, ships, and all objects made of metal, especially that iron. will lose crores of rupees every year on coconut on account of corrosion. In corrosion, metal oxide by loss of electron and oxygen for formation of oxide. Corrosion of iron, commonly known as rusting, occur in presence of water and air. The chemistry of corrosion is quite complex, but it may be considered essentially as an electrochemical phenomenon. At a particular spot, figure 2.13, an object made of iron oxidation takes place, and that spot behaves as anode, and we can write the reaction. Anode 2Fe solid form 2Fe 2 plus 4 electron. E naught Fe 2 plus Fe form A is equal to 0.44 volt. Oxidation half reaction Fe form Fe2 plus, reduction of reaction oxygen form H2O2. Electron released at anode spot move the metal and go to another spot on the metal and reduce oxygen in the presence of H plus, which is believed to oxygen from H2CO3 formed due to dissolution of carbon dioxide from air into water. Hydrogen ion in water may also be available due to dissolution of other acid oxide from the atmosphere. This is what we have as cathode with reaction. Cathode O2 gas from plus 4H plus aqueous plus 4 electron form 4H2. Overall reaction Fe plus O2 plus 4H plus Fe2 plus 4 2H2O plus E naught cell. E naught cell is equal to 1.67 volt. The ferrous ion further oxidized to atmospheric oxygen to ferric ion, which come out to rust and form hydrated ferric oxide, FeO3 dot XH2, and with further production of hydrogen ion. Prevention of corrosion is prime importance. It is not only save money but also help in preventing accidents such as bridge collapse or failure of key component due to corrosion. One of the simplest methods of preventing corrosion is prevent surface metallic object in contact with surface atmosphere. This can be done by covering the surface with paint or by some chemical by bisphenol. Another simple method to cover surface of metal, zinc, by other metals, there is SN zinc, etc., that are inert and or react to save other object. An electrochemical method is to provide sacrificial electrode to another metal like magnesium, zinc, etc., which corrode itself but save the object. Hydrogen economy. At present, main source of energy is driving economy is fossil fuels such as coal, oil, and gas. As more people on the planet aspire to improve their standard of living, their energy requirement increases. In fact, per capita consumption of energy used in measures to development. Of course, it is assumed that energy used for productive purpose are not merely wasted. We are already aware that carbon dioxide produced by combustion of fossil fuels resulting in greenhouse effect. This leading to rise in the temperature of Earth's surface, causing polar ice melts and ocean levels to rise. This will flood low-lying areas along coast, and some island nations such as Maldives face total submergence. In order to avoid such catastrophe, we need to limit our use of carbonaceous fuel. Hydrogen provide an ideal alternative for combustion, alternate to water only. Hydrogen products must come from splitting water using solar energy. Therefore, hydrogen can be used as a renewable and non-polluting source of energy. This is vision of hydrogen economy. Both the production of hydrogen and electrolysis of water and hydrogen combustion of fuel will be important in the future, and both these technology are based on electrochemical principle. Summary: electrochemical cell consists of two metallic electrode dipping in electrolytic solution. Thus, the important component of electrolytic chemical cell is ionic conductor electrolyte. Electrochemical cell are important type. The galvanic cell energy A chemical energy of the spontaneous redox reaction is converted into electrical work, whereas the electrolytic cell electrical energy is converted into non-spontaneous redox reaction. The standard electrode potential of any electrode dipping in appropriate solution is defined with respect to standard electrode potential hydrogen electrode taken as zero. The standard potential of cell is obtained by taking difference to standard potential cathode and anode. E naught cell is equal to E cathode minus E anode. The standard potential of the cell are related. Standard gives free energy delta G naught is equal to minus NF E naught, and equilibrium constant related to gives free delta G naught is equal to minus RT ln K. For reaction taking place in the cell, concentration dependence of potential electrode of cell given by Nernst equation. The conductivity K of electrolytic solution depends on concentration of electrolyte, nature of solvent and temperature. Molar conductivity lambda m is defined by K by C, where C is concentration. Conductivity decreases but molar conductivity increases with decrease in concentration. It increases slowly with decrease in concentration for strong electrolyte, while increase in very steep of weak electrolyte, very dilute solution. Kohlrausch found that the molar conductivity at infinite dilution for electrolyte is the contribution of the molar conductivity of ion which dissociate it is known as law of independent migration of ion. And for many applications, ion conduct electricity through solution, but oxidation and reduction of ion take place at the electrode in an electrochemical cell. Batteries and fuel cells are very useful to form galvanic cells. Corrosion of metal is essentially an electrochemical phenomenon. Electrochemical principles are relevant to hydrogen economy. So, electrochemistry unit 2 completed. अब अपन करेंगे केमिकल काइनेटिक्स चैप्टर 3. इसके लिए अपन लेते हैं 156 to 12:05 AM ब्रेक. नहीं करना भरोसा मुझे अब किसी पे, जिसे जाना हो वो चला जाए जिंदगी से। अब तो मुझे घंटा फर्क नहीं पड़ता है। जिसे जाना हो वो चला जाए जिंदगी से, जिसे जाना है वो आएगा वो जिंदगी में। अब तो मुझे घंटा फर्क नहीं पड़ता है। तो जिसे जाना हो वो चला जाए जिंदगी, जैसे आना हो वो आएगा वो जिंदगी में। अब तो मुझे घंटा फर्क नहीं पड़ता है। सो वेलकम बैक मेरे भाई। टाइम हो गया 2:05 हो गया। अपने चैप्टर स्टार्ट करना है इलेक्ट्रोकेमिस्ट्री। लेट्स गो। केमिकल काइनेटिक्स। केमिकल sorry chemical kinetics help us in understanding how chemical reaction occur. Chemistry by its very nature is concerned with change. Substances with well-defined properties are converted by chemical reaction into other substances with different properties. For any chemical reaction, chemists try to find out first the feasibility of chemical reaction, which can be predicted by thermodynamics, as you know that a reaction with delta G less than 0 at constant temperature and pressure is feasible. B. Extent to which a reaction will proceed can be determined from which chemical equilibrium. C. Speed of reaction, that is time taken by reaction to reach equilibrium. Along with feasibility and extent, it is equally important to know the rate and the factor controlling the rate of the chemical reaction for its complete understanding. For example, which parameters determine as to how rapidly food gets spoiled, how to design a rapidly setting material for dental filling, or what controls the rate at which fuel burns in an auto engine. All these questions can be answered by the branch of chemistry which deal with the study of reaction rates and their mechanism, called chemical kinetics. The word kinetics is derived from Greek words kinesis, meaning movement. The thermodynamics tell only about feasibility of a reaction, whereas chemical kinetics tell us the rate of a reaction. For example, the thermodynamic data indicate that diamond shall convert to graphite, but in reality conversion rate is very slow, that the change is not perceptible at all. Therefore most people think that diamond is forever. Kinetic studies not only help us to determine the speed or rate of a chemical reaction but also describe the condition by which the reaction rate can be altered. The factors such as concentration, temperature, and pressure and catalyst affect the rate of reaction. At the microscopic level, we are interested in amount of reacted are formed and the rates of their consumption or formation. At a molecular level, the reaction mechanism involving orientation and energy molecule undergoing collision are discussed. In this unit, we shall be dealing with the average and instantaneous rate reaction and the factor affecting this. Some elementary ideas about collision theory of reaction rates are also given. However, in order to understand all these, let us first learn about the reaction rate. 3.1 Rate of chemical reaction. Some of the reactions, such as ionic reaction, occur very fast. For example, precipitation of silver chloride occurs instantaneously by mixing of aqueous solution of silver nitrate and sodium chloride. On the other hand, some reactions are very slow. For example, rusting of iron is presence of air and moisture. Also, are reaction like inversion of cane sugar and hydrolysis of starch, which proceed with moderate speed. Can we think of more example of each category? You must know that speed of automobile is experienced in terms of change in position or distances covered by it in a certain period of time. Similarly, the speed of reaction or the rate of a reaction can be defined as the change in concentration of reactant or product in unit time. To be most scientific, to be more specific, it can be expressed in terms of first, rate of decrease in concentration of any one of the reactant, or second, the rate of increase in concentration of any one of the product. Consider the hypothetically reaction assuming that the volume of system remain constant. Reactant change into product. 1 mole of reactant R produce 1 mole of product. If R1 and R1 and P1 is the concentration of R reactant and product respectively at time T1, and R2 and P2 are the concentration at time T2, then delta T1 is equal to delta T2 minus delta N2 T1, delta is equal to R2 minus R1, and delta P is equal to P2 minus P1, concentration of P2 minus concentration of P1. The square bracket in expression used to express molar concentration. Rate of disappearance of R is equal to decrease in concentration of R by delta T. Rate of appearance of P product is equal to rate of concentration of product by time taken is equal to plus delta P by delta D. Since delta R is negative quantity, as concentration of reactant is decreasing, it is multiplied with minus 1 to the reaction in positive quantity. Equation 3.1 and 3.2 given above represent the average rate of reaction. R average. Average rate depends upon change in concentration of reactant or product and time taken for changing change to occur. 3.1 Instantaneous and average rate of reaction. A. Time concentration of reactant. R average is equal to delta R naught delta R by delta T, and R instantaneous is equal to minus dr by dt and is equal to minus slope. This is time and this is concentration of product, and R instantaneous is equal to dp by dt is equal to slope, and R average is equal to delta p by delta t, concentration of P2 minus concentration of P1 by T2 minus T1. Units of rate of reaction. From equation 3.1 to 3.2, it is clear that the unit of rate of concentration per unit time, for example, in concentration is in mole per liter and time is in second, then the unit will be mole per liter per second. However, in gaseous reaction, when the concentration of gases is expressed in terms of their partial pressure, then the units of rate will be atmosphere per second. Average rate of hydrolysis of butyl chloride. Here is butyl chloride mole per in mole per liter, and T1 T2 per second. R average. It can be seen in table 3.0. Average rate of fast from 1.90 into 10 power minus 4 mole per second to 0.4 into 10 power minus 4 mole per liter per second. However, average rate cannot be used to predict the rate of reaction at a particular instant, as it would be constant for the time interval for which it is calculated. So, to express the rate of particular moment of time, we determine the instantaneous rate. It is obtained when we consider the average rate at the smallest time interval, say dt, that is when delta t approaches to 0. Hence, mathematically, for an infinitesimally small dt, instantaneous rate is given by R average is equal to delta R by delta t is equal to delta p by delta t, as delta t tends to 0, or R instantaneous is equal to minus dr by dt is equal to dp by dt. Here butyl chloride and it is time. This is instantaneous rate given by dp by dt. Instantaneous rate of hydrolysis of butyl chloride C4H9Cl. It can be determined graphically by drawing the tangent at time t on either of curves of concentration R and P versus time t, and calculating its slope. So in figure 3, in problem 3.1, R instantaneous is 600. For example, can be calculated by plotting concentration of butyl chloride as a function of time. A tangent is drawn that traces a curve at t is equal to 600 second. The slope of this tangent gives instantaneous rate. So R instantaneous is equal to 600 mole per liter is equal to 5.12 into 10 to the power minus 5 mole per liter per second, and t is equal to 250 second. R instantaneous is and so on. Now consider the reaction Ag plus Cl2 from AgCl2, where stoichiometric coefficient of the reactant and product are same. Then the rate of reaction is given as rate of reaction is equal to minus delta Hg by delta T is equal to minus delta Cl2 by delta T is equal to minus into delta AgCl2 by delta T. That is, rate of disappearance of any of the reactant is same as the rate of appearance of product. But in the following reaction, the 2 moles of HI decomposes to produce 1 mole of H2 and HI. 2HI gas plus 2H2 gas plus HI gas. For expressing the rate such a reaction, whether stoichiometric coefficient of reactant and product are not equal to 1, a rate of disappearance of any of these reactant or rate of appearance of the product is divided by their respective stoichiometric coefficient. Since rate of consumption of HI is twice to the rate of formation of H2 and HI2, to make them equal, the term delta HI is divided by 2. The rate of reaction is given by rate of reaction is equal to half delta HI by delta T is equal to delta H2 by H2 delta T is equal to delta I2 by delta T. Similarly, for the reaction 5Br minus plus BrO5 plus 6H2 equals 3Br2 plus 3H2O, rate is equal to minus 1 by 5 Br minus delta T is equal to minus Br03 by delta T is equal to minus 1 by 6 delta S by delta T is equal to 1 by 3 delta Br2 by delta T and 1 by 3 delta S2 by delta T. For gaseous, reaction at constant temperature concentration is directly proportional to partial pressure of species. Hence, rate can be expressed as the rate of change of partial pressure of reactant and product. 3.2 factor influencing rate of reaction. Rate of reaction depends upon the experimental conditions such as concentration of reactant, pressure in case of gaseous, temperature and catalyst. 3.2.1 dependence of rate on concentration. The rate of chemical reaction at given temperature may depends on the concentration of one or more reactant and product. The representation of rate of reaction in terms of concentration of the reactant is known as rate law. It also called rate equation or rate expression. 3.2.2 rate expression and rate constant. The result in table 3.1 clearly shows that rate of reaction decreases within the passage of time as the concentration of reactant decreases. Conversely, rates generally increase when reactant concentration increases, so rate of reaction depends upon concentration of reactant. Consider in general A plus BB forms C plus DD, where A, B, C and D are stoichiometric coefficient of reactant and products. The rate expression for this reaction is rate directly proportional to A to power x b power y, where exponent x and y may or may not be equal to the stoichiometric coefficient A and B of the reactant. Above equation can also be written as rate is equal to K A to power x B to power y minus dr by dt is equal to K x to power y x to A to power x B to power y. For this form of equation 3.4b is known as a differential rate equation, where K is proportionality constant called rate constant. The equation like 3.4 which relate the rate of reaction concentration of reactant is called rate law or rate expression. Thus, rate law is the expression in which reaction rate is given in terms of molar concentration of reactant, with each term rise to some power which may or may not be same to as a stoichiometric coefficient for reacting species is balanced in chemical reaction. For example, 2NO2 plus O2 form 2NO2 gas. We can measure the rate of reaction as function of initial concentration, either by keeping concentration of one of the reactant and constant, changing concentration of other reactant by changing the concentration of other reactant. The following resultant is obtained. Initial rate of formation of NO2, the NO2 and NO2. It is obvious after looking at the result that when concentration of NO is doubled and that of O2 is kept constant, then initial rate increases by factor of 4 from 0.096 to 0.384 mole per liter per second. This indicates that the rate depends upon the square of the concentration of the NO. When concentration of NO is kept constant and concentration of O2 is doubled, the rate also gets doubled, indicating that rate depends upon concentration of O2 on to the first power. Hence, the rate equation for this equation will be rate is equal to KNO square O2. The differential form rate equation expression as given below. dr by dt is equal to KNO to power 2 and O2. Now we observe that the reaction in rate equation derived from experimental data, the exponent of the concentration term are the same as the stoichiometric coefficient in balanced chemical equation. Some other examples given below: reaction CH3Cl3 chloroform plus chlorine forms carbon tetrachloride from HCl. Rate KCl CH3 and Cl2 power half. CH3 C11O C2H5 plus H2O forms CH3 C11OH plus C2H5OH. Rate is equal to CH3 C11OH C2H5 and H2O to power 0. In this reaction, the exponents of concentration term are not same as the stoichiometric coefficient. Thus, we can say that rate law of any reaction cannot predict the merely looking at balanced chemical equation. Therefore, theoretically must be determined experimentally.
3.2.3 order of reaction. In the rate of reaction 3.4, the rate k is equal to a to power x plus b to power I. X and y indicate how sensitive the rate is to change in concentration of a and b. Sum of these exponents x plus y in 3.4 gives the overall order of reaction, whereas x and y represent the order with respect to reactant a and b respectively. Hence, the sum of powers of concentration of the reactant and rate law expression is called order of that chemical reaction. Order of reaction can be 0, 1, 2, 3 or even fraction. A zero order reaction means that the rate of reaction independent of the concentration of reactant. A balanced chemical equation never gives us a true picture of how a reaction takes place, since rarely a reaction gets completed in one step. The reaction taking place in one step are called elementary reaction. When a sequence of elementary reaction called mechanism gives us the product, the reaction is called complex reaction. These may be consecutive reaction, that is oxidation of ethane to carbon dioxide and water passes through series of intermediate reaction which in which alcohol, aldehyde and acid is formed. Reverse reaction is upside reaction, that is nitrogen to phenol yields orthonitrophenol and pyranitrophenol. Units of rate constant. For general reaction, AA plus BB forms CC plus DD. Rate K, A to power X, B power Y, where X plus Y is equal to N. Order of reaction, K is equal to rate Y, A to power X, B to power Y is equal to concentration by time into 1 by concentration upon air, where A is equal to B. Taking a SI unit of concentration mole per liter, the time S and time S, the unit of K for different reaction order listed below. For zero order reaction, order 0, unit of rate constant mole per liter per second. First order reaction, order 1, unit is per second, and second order reaction, order 2, unit is mole inverse liter second inverse. 3.2.4 molecularity of a reaction. Another property of reaction called molecularity help in the understanding its mechanism. The number of reacting species, atom, ion or molecule taking place in elementary reaction, which must collide simultaneously in order to bring about chemical reaction, in order to molecularity of reaction. The reaction can be unimolecular when the reacting species involve, example, decomposition of ammonium nitrate, NH4NO2 form N2 plus 2H2O. Bimolecular reaction involves simultaneously collision between two species, for example, dissociation of hydrogen iodide. Trimolecular or tetramolecular reaction involves simultaneously collision between three reacting species, for example, 2NO plus O2 form 2NO2. The probability that more than three molecules can collide react simultaneously is very small. Hence, reaction with the molecularity 3 are very rare and slow to proceed. It is therefore wide evident that complex reaction involving more than three molecules in the stoichiometric equation must take place in more than one step. KClO3 plus 6FeSO4 plus 2H2SO4 form KCl plus 3FeSO4 whole thrice plus 3H2O. This reaction, which apparently seems to be 10th order, is actually a second order reaction. This shows that this reaction takes place in several steps. Which step control the rate of overall reaction? The question can be answered if we go through mechanism of reaction. For example, chances to win relay race competition by a team depends upon slowest person in the teams. Similarly, overall rate of reaction is controlled by slowest step in a reaction called rate determining step. Consider the decomposition of hydrogen peroxide, which is catalyzed by iodide ion in alkaline medium. H2O2 in presence of I minus alkaline medium form H2O plus O2. Rate of this reaction is rate is equal to minus dH2O2 by dt KH2O2 I minus. This reaction is first order with respect to H2O and I minus. Evidence says that this reaction takes place in two steps. H2O2 I minus form H2O plus IO minus, H2O2 plus IO minus 5H2O I minus plus O2. Both the step bimolecular elementary reaction. Species IO minus is called intermediate since formed during course of reaction but not overall balance equation. The first step being slow is not the rate determining step. Thus, the rate of formation of intermediate will determine the rate of reaction. Thus, from the discussion till now, we concluded that the following: first, order of reaction is an experimental quantity. It can be 0 and even the fraction, but molecularity cannot be 0 or non-integer. Second, order is applicable to elementary as well as complex reaction, whereas molecularity is applicable only for elementary reaction. For example, reaction of molecularity has no meaning. Third, complex reaction order is given by slowest step and molecularity of slow step is given in order to overall reaction. 3. Integrated rate law. We have already noted a concentration dependence of rate is called differential rate equation. It is not always convenient to determine the instantaneous rate, as it is measured by determination of slope of tangent at point t in the concentration versus time plot. This makes it difficult to determine the rate law and hence the order of reaction. In order to avoid this difficulty, we can integrate the differential rate equation to give relationship between directly measured experimental data, that is concentration at different time, and rate constant. The integrated rate equation are different from reaction of different reactive orders. We shall determine this equation only for 0 and first order chemical reaction. 3.3.1 Zero order reaction. Zero order reaction means that reaction takes place in proportion to 0 power of concentration of reactant. Consider the following reaction: rate reactant change in product. Rate is equal to minus dr by dt is equal to k r to power 0. As any quantity rise to power 0 is unity, rate is equal to minus dr by dt k into 1. Dr is equal to minus k dt. Integrating both sides, r is equal to minus kt by I plus I, where I is the constant of integration. At t is equal to 0, concentration of reactant R is equal to R naught, where R naught is the initial concentration of the reactant. Substituting in the equation 3.5, R naught is equal to minus k into 0 plus I, R naught is equal to I. Substituting the value of I in equation 3.5, R is equal to minus kd plus R naught. Comparing with 3.6 equation of a straight line y is equal to mx plus c, if we plot r against t, we get the straight line with slope minus k. Intercept is equal to r naught. Further simplifying the equation 3.6, we get a constant k is equal to r naught minus k. Variation of concentration of versus time in plot zero order reaction. So this is time and this is concentration, and this intercept is r naught and slope k naught. Zero order reaction is relatively uncommon, but they occur under special conditions. Some enzyme catalyze reaction and reaction which occur on metal surface are few examples of zero order reaction. The decomposition of gaseous ammonia or hot platinum on hot platinum surface is zero order reaction at high pressure. 2NH3 gas at 1130 Kelvin platinum catalyst form N2 gas plus 3H2 gas. Rate is equal to KNH3 to power 0 is equal to K. In this reaction, the platinum metal acts as catalyst at high pressure. The metal surface get saturated with gas molecule, so a further change in reaction condition is unable to alter the amount of ammonia on surface of catalyst, making rate of reaction independent of its concentration. The thermal decomposition of Hi on gold surface is another example of zero order reaction. 3.3.2 First order reaction. In this class of reaction, the rate of reaction is proportional to the first power of concentration of reactant R. For example, reactant change in product rate is equal to minus dr by dt is equal to kr. dr by r is equal to minus k dt. Integrating this equation, we get ln r is equal to minus kt plus I. Again, I is constant of integration value can be determined easily when t is equal to 0, r is equal to r naught, where r naught is initial concentration of reactant. Therefore, equation 3.8 written as ln r naught is equal to minus k into 0 ln r is equal to I naught I. Substituting the value of I from equation 3.8, ln r is equal to minus kt ln r naught. Rearranging ln r by r naught is equal to minus kt, k is equal to 1 by t ln r naught by r. At time t1, the reaction ln r1 is equal to minus k t1 ln r naught, and at time t2 ln r2 is equal to minus kt plus ln r naught, where r1 and r2 are concentration of reactant at different time t1 and t2. Subtracting 3.12 from 3.11, Rn r1 plus Rn r2 is equal to minus k t1 minus k t2. ln r1 by r2 is equal to k t2 minus t1. K is equal to 1 by t2 minus t1 ln r1 by r2. Equation 3.9 can also be written as ln r by r naught is equal to minus kt. Taking anti-log on both sides, r is equal to r naught e to power minus kt. Comparing equation 3.9 with y is equal to mx plus c, we plot ln r against t. We get a straight line with slope minus k and intercept equal to ln r. The first order of rate of reaction 3.10 can also be written as in the following form: k is equal to 2.303 t log r naught by r. Log r naught by r is equal to kt by 2.303. If we plot graph between log r naught by r versus t, the slope k by 2.303. Hydrogenation of ethene is an example of first order reaction. C2H4 gases plus H2 gas forms C2H6 gas. Rate is equal to k C2H4. All natural and artificial radioactive decay unstable nuclei take place in first order of kinetics. A plot of ln r and t for first order of reaction. This is ln r and this is time. This is ln r naught and this is slope minus k. Plot of r ln r naught by r was a time for first order reaction. Log r naught by r and time, this slope is equal to k by 2.303. Rate k is equal to Rn. Decomposition of N2O5 and N2O are some example of first order reaction. Let us consider typical first order gas phase reaction. Ag gas form B gas plus carbon gas. Let P initial be initial pressure and of A, and Pt is total pressure at time t. Integrated rate equation of such equation can be derived as total pressure P total Pa plus Pv plus Pc pressure unit. Pa, Pv and Pc are partial pressure of A, B and C respectively. If X atm is be the decrease in pressure of time t at time t, and 1 mole of each B and C is being formed, the increase in pressure of B and C will also be X atmospheric each. At t is equal to 0, P initial atmospheric pressure, B P atmospheric and C 0 atmospheric pressure. At time t, this is P initial minus X atmospheric pressure, this is X atmospheric pressure, and this is at X, and P total is equal to P initial minus X plus X is equal to P I minus Pi plus X. X is equal to P total minus P initial. Pi is equal to Pi minus X is equal to Pi minus Pt minus Pi. 2Pi is minus Pt. K is equal to 2.303 by T log Pi by Pa. K is equal to 2.303 T log Pi by 2Pi minus P total. 3.3.3 half-life reaction. The half-life of a reaction is the time in which the concentration of a reactant is reduced to 1/2 of initial concentration. It is represented by T half. For zero order reaction, the rate constant is given in equation 3.7. K is equal to R naught minus R by T. T is equal to T half. R is equal to half R naught. The rate constant at T half become K is equal to R naught minus 1 by 2 R naught by T half is equal to R naught by 2K. It is clear from T half for zero order reaction is directly proportional to initial concentration of reactant as inversely proportional to rate constant. For first order reaction, K is equal to 2.003 T log R naught by R, T half is equal to R naught by 2. The above reaction becomes K is equal to 2.303 T half log R naught by R by 2. T half is equal to 2.303 by K log 2. T half is equal to 2.303 by K into 3.301. T half is equal to 0.693 Kelvin. It can be seen for the first order reaction half life period is constant. It is independent of initial concentration of reacting species. The half-life of first order equation is readily calculated from the rate constant and vice versa. For zero order reaction, T half directly proportional to R naught. For first order reaction, T half is independent of R naught. The order of reaction is sometimes altered by condition. There are many reactions which obey first order rate although they are higher order reaction. Consider the hydrolysis of ethyl acetate, which is chemical reaction between ethyl acetate and water. In reality, it is second order reaction, and concentration of both ethyl acetate and water affect the rate of reaction. But water is taken in large excess for hydrolysis. Therefore, concentration of water is not altered much during the reaction. Thus, the rate of reaction is affected by concentration of ethyl acetate only. For example, during hydrolysis of 0.01 mole of ethyl acetate with 10 mole of water, amount of the reactant and product are at the beginning. The completion T, the reaction is given as below. At T is equal to 0, the ethyl acetate is 0.01 mole and H2O is 10 mole, and this is 0 mole, and this is ethanol is 0 mole. At T is equal to 0, at T time, this is 0 mole, 0.999 mole, this is 0.0901 mole, and this is 0.01 mole. The concentration of water does not get altered much during the course of reaction, so the reaction behaves as first order of reaction. Such reaction is called pseudo first order reaction. Inversion of cane sugar and pseudo first order reaction. Cane sugar C12H22O11 plus H2O form glucose plus fructose. Rate is equal to K C12H22O11. Temperature dependence of rate reaction. Most of chemical reaction is accelerated by increase in temperature. For example, decomposition of N2O5. The time taken for half the origin of amount of material to decompose in 12 minutes at 50 degrees Celsius, 5 hours at 25 degrees Celsius, and 10 hours at 0 degrees Celsius. You also know that mixture of potassium permanganate KMnO4, the oxalic acid C2H2O5, potassium permanganate get decolorized faster at higher temperature than that of lower temperature. It has been found that for chemical reaction with rise in temperature by 10 degrees Celsius, rate constant is nearly doubled. The temperature dependence of rate chemical reaction can accurately explained by Arrhenius equation. It was first proposed by Dutch chemist J.H. van Hoff, but Swedish chemist Arrhenius provided physical significance, justification, and interpretation. K is equal to e to the power minus Ea by RT, where A is Arrhenius factor. For frequency factor, it is also called pre-exponential factor. It is also specific to a particular reaction. R is gas constant and E is activation energy measured in joule per mole. It can be understood clearly using following reaction. H2 plus I2 gas form 2H2 2HI gas. According to Arrhenius, this reaction can take place only when a molecule of iodine collide to form an unstable intermediate. It exists for very short time and then break up to form two molecules of hydrogen iodide. Formation of HI through intermediate. The energy required for this intermediate called activated complex C, known as activation energy EA. Figure 3.7 obtained by plotting potential energy versus reaction coordinate. Reaction coordinate represent the profile of energy change when reactant change into product. Some of the energy released when the complex decomposes to form product. So the final enthalpy of reaction depends upon nature of reactant and product. Diagram showing the plot of potential energy versus reaction coordinate. Reaction coordinate, and this is potential energy. This is activation energy and activated complex, and 2Hi plus H2 plus Hi, and this is delta H. All the molecules in the reaction species do not have same kinetic energy, since it is difficult to predict the behavior of any one molecule with precision. Ludwig Boltzmann and James Clerk Maxwell used to statically predict the behavior of large number of molecules. According to them, the distribution of kinetic energy may be described by plotting the fraction of molecule E, Ne, and by Nd when given kinetic energy E versus kinetic energy. Here Ne is the number of molecules with energy E, and Nd is the total number of molecules. Distribution of curve showing energy among gaseous molecule, kinetic energy, and this is fraction of molecule, and this is most probable kinetic energy. The peak of curve correspond to most probable energy, kinetic energy, maximum fraction. There is decreasing number of molecule with energy higher to lower than is this value. When the temperature rises, the maximum of the curve moves to higher energy value, and curve broadens out, that is spread to the right, such that there is greater proportion of molecules which much higher energy. The area under curve must be constant, since the total probability must be 1 at all time. We can mark the position Ea on Maxwell-Boltzmann distribution curve. Distribution of curve showing temperature dependence of rate reaction, kinetic energy, fraction of molecule, and this is time taken by molecule without catalyst, and after catalyst energy of activation. Area showing fraction of molecule reactive is time t. Area of fraction showing addition molecule which react with time t plus 10. Increase in temperature of substrate increasing the fraction of molecule which collide with energy is greater than E naught Ea. It is clear from the diagram that in the curve at t plus 10, the area showing the refraction of molecule having energy equal to greater than activation energy get double, leading to the double rate of reaction. In Arrhenius equation 3.18, the factor e to power minus A by RT correspond to the fraction molecule that have kinetic energy greater than Ea. Taking natural logarithm of both side equation 3.18, ln k is equal to minus A by RT ln A. The plot of ln k versus 1 by t gives a straight line according to equation 3.91 or 3.19 as shown in figure 3.10. Thus, it has been found that Arrhenius equation 3.18 that increasing the temperature of decreasing activation energy will result in increasing rate of reaction exponentially with increasing rate constant. A plot between k and ln k and half t. This is ln k and this is half t. Slope minus A by r. This is intercept ln. Figure 3.10 slope minus A by r, the intercept ln A. So we can calculate E and A using this value. At temperature T1 equation 3.19 is ln K1 is equal to minus A by RT ln A. At temperature T2 equation 3.19 ln K2 is equal to minus A by RT2 plus ln K. Since A is constant for given reaction, K1 and K2 are given value rate constant as temperature T1 and T2 respectively. Subtracting the equation from 3.21, we obtain ln K2 minus ln K1 is equal to minus A by RT1 minus A by RT2. ln K2 by K1 is equal to E by RT 1 by T1 minus 1 by T2. Log K2 by K1 is equal to EA by 2.303 by R 1 by T1 minus 1 by T2. Log K2 by K1 is equal to EA by 2.303 by R T2 minus T1 RT T2 minus T1 by T2. 3.4 Effect of catalyst. A catalyst is a substance which increases the rate of reaction without itself undergoing any permanent chemical change. For example, MnO2 catalyzes the following reactions so as to increase the rate of reaction considerably. KClO3 MnO2 form 2KCl plus 3O2. The word catalyst should not use when the added substance reduces the rate of reaction. The substance is then called inhibitor. The action of catalyst can be explained by intermediate complex theory. According to this theory, a catalyst participates in chemical reaction by forming temporary bond with reactant resulting in the intermediate complex. This has transitory existence and decomposes to yield product and catalyst. It is believed that the catalyst provides an alternative pathway of reaction mechanism by reducing the activation energy between reactant and product, hence lowering the potential energy barrier as follows in figure 3.14. Effect of catalyst in activation reaction coordinate, and this is potential energy, and this is reactant and this is product, and this is reaction path with the help of catalyst, and reaction without path of catalyst. This is energy of activation with catalyst, and this is energy of activation without catalyst. It is clear from Arrhenius equation 3.1 that lower the value of activation energy, faster will be the rate of reaction. A small amount of catalyst can catalyze a large amount of reactant. A catalyst does not alter Gibbs energy delta G of reaction. It catalyzes the spontaneous reaction but does not catalyze non-spontaneous reaction. It is also found that a catalyst does not change equilibrium constant of reaction, rather it helps in attaining equilibrium faster. That is, it is catalyzes forward as well as backward reaction to the same extent so that equilibrium state remains same but reaches earlier. Collision theory of chemical reaction. Through Arrhenius equation is applicable under a wide range of circumstances. Collision theory, which developed by Max Torres and William Lewis in 1960-18, provide a greater insight into the energetics and mechanicistic aspect of reaction. It is based on kinetic theory of gases. According to this theory, reactant molecules are assumed to hard sphere and reaction postulated to occur when molecules collide with each other. The number of collisions per second per unit volume of a reaction mixture is known as collision frequency Z. Another factor which affects the rate of chemical reaction is activation energy, as we have already studied for biomolecular elementary reaction. A plus B form product rate of reaction can be expressed as rate ZAV is equal to e power minus EA by RT, where ZA represents collision frequency of reactant A and B, and e to power minus EA by RT represents the fraction molecule with energy is equal to greater than EA. Comparing 3.23 with Arrhenius equation, we say that a related collision frequency. Equation 3.23 predict the value of rate constant fairly accurately for the reaction that involve atomic species or simple molecules, but for complex molecules significant deviation are observed. The reason could be that all collisions do not lead to the formation of product. The collision in which molecules collide with sufficient kinetic energy called threshold energy and proper orientation so as to facilitate breaking of bonds between reacting species and formation of new bond to form product called effective collision. For example, formation of methanol and bromoethane depends upon orientation of reactant molecule as shown in figure 3.12. The proper orientation of reactant molecule led to bond formation, whereas improper orientation make them simply bounce back and no product are formed. Diagram showing molecule having proper improper orientation. So this is improper orientation and this is proper orientation, no product formed, and in this case product is formed. The account of effective collision rate of factor P, called probability or steric factor, is introduced. It takes into account the fact that in a collision molecules must be properly oriented, that is rate is equal to PZA e to power minus EA by RT. Thus the collision theory activation energy and further and proper orientation of molecule together determine the criteria of effective collision and hence the rate of chemical reaction. Collision theory also certain drawback as considering atoms molecule to be hard sphere and ignore their structure aspect. You will study detail this theory in more and more theory in your higher classes. Summary: chemical kinetics is the study of chemical reaction with respect to reaction rates, effects of various variable rearrangement of atoms and formation of intermediates. The rate of reaction is concerned with increase in orientation of rates and or increase in concentration of product per unit time. It can be expressed as instantaneous rate of particular instance of time and average rate over a large interval of time. A large number of factors such as temperature, concentration, reactant, catalyst affect the rate of reaction. Mathematically, representation of rate reaction is given by rate law. It has to become determined experimentally and cannot be predicted. Order of reaction with respect to reactant is the power of concentration which appear in rate law equation. The order of reaction is the sum of all the power concentration from different reactants. Rate constant is proportionality factor in the rate law. A rate constant in order to reaction can be determined from rate law and the integrated rate equation. Molecularity is defined only for elementary reaction. Its value is limited from 1 to 3, whereas order can be 0, 1, 2, 3 or even fraction. Molecularity or order elementary reaction are same. Temperature dependence on rate constant described Arrhenius equation k is equal to a to power k is equal to a e to power minus a by rt. A correspond to activation energy and given by the energy difference between activated complex and reactant molecule, and a Arrhenius factor and pre-exponential factor correspond to collision frequency. The equation clearly shows that increase of temperature, lowering of EA will lead to increase in rate of reaction, and always catalyst lower the activation energy by providing alternate path of the reaction. According to collision theory, another factor P called steric factor, which refer to orientation of molecule which collide, contribution to effective collision, modify the Arrhenius equation to k is equal to pzab to power minus eart. So chemical kinetics completed. We'll start D and F block. So unit 4 is D and F block elements. So 2:54 to 3 am break. मेरे रास्ते कमर तो न पहने नजर, ये नजर से मिल ये नजर, मेरे रास्ते कमर तो न पहने नजर। रोहन बुजाड़ भाई का कमेंट आया था, आप समझते भी हैं? तो हाँ भाई, समझते भी हैं, लेकिन कुछ टॉपिक होता है इसमें, हर एक टॉपिक नहीं रीडिंग करते हैं सिर्फ, और इसमें क्या है, मतलब हर एक टॉपिक इसमें नहीं समझ सकते हैं, लेकिन कुछ जो इम्पोर्टेंट टॉपिक है या जो हाईलाइटेड टॉपिक है वो उसमें रिवाइज हो जाता है। बाकी लेकिन समझने के लिए तो पूरा डिटेल करना पड़ेगा ना, और क्वेश्चन करना पड़ेगा। ये रिवीजन टाइप में करते हैं ऐसे, रिवीजन हो जाता है एक तरीक़ा से इससे। और हाँ, लाइव है भाई ये। भाई तो चैप्टर स्टार्ट होने के बाद मैं कमेंट नहीं पढ़ता हूँ, इसीलिए चैप्टर एंड होने के बाद ही 5 मिनट का जो रेस्ट मिलता है उसी में कमेंट कर दिया करो भाई लोग, क्योंकि चैप्टर स्टार्ट करने के एंड तक नहीं करते हैं। टाइम हो गया, स्टार्ट करते हैं भाई, 1 मिनट। सो भाई लेट्स गो। टाइम हो गया भाई। वेलकम बैक टू आवर एनसीईआरटी रीडिंग सीरीज। अभी अपन पढ़ेंगे डी एंड एफ ब्लॉक एलिमेंट्स। तो भाई देखो, किसी भी कोचिंग में पढ़ो, किसी भी इंस्टीट्यूट में पढ़ो, किसी भी टीचर से पढ़ो, डी एंड एफ ब्लॉक का तो एनसीईआरटी पढ़ते ही हो भाई लोग। तो चलो आज साथ में पढ़ते हैं। यूनिट 4 डी एंड एफ ब्लॉक elements. Iron, copper, silver and gold among the transition element that have played important roles in development of human civilization. The inner transition elements such as thorium, protactinium, uranium are proving excellent sources of nuclear energy in modern times. The D block of periodic table contains elements of group 3 to 12 in which the d orbitals are progressively filled in each of the 4 long periods. The F block consists of elements in which 4f and 5f orbitals are progressively filled. They are placed in a separate panel at bottom of periodic table. The name transition metal and inner transition metals are often used to refer the elements of D and F block respectively. There are mainly 4 series of transition metals: 3D series scandium to zinc, 4D series yttrium to cadmium, 5D series lanthanum to hafnium to mercury, and 6D series has actinium and elements from rutherfordium to copernicium. The 2 series of inner transition metal, that is 4f cerium to lutetium and 5f thorium to lawrencium, are known as lanthanoids and actinoids respectively. Originally, the name transition metal was derived from the fact that their chemical properties were transitional between those S and P block elements. Now, according to IPAC, transition elements are defined as metal which have incomplete d subshell either in neutral atom or in their ions. Zinc, cadmium and mercury of group 12 have full D10 configuration in their ground state as well as in their common oxidation state, and hence are not regarded as transition metals. However, being the end members of 3D and 4D 5D transition series respectively, their chemistry is studied along with chemistry of transition metals. The presence of partially filled D and F orbitals in their atoms make transition elements different from that of the non-transition elements. Hence, the transition elements and their compounds are studied separately. However, the usual theory of valence as applicable to non-transition element can be applied successfully to the transition element also. Various precious metals such as silver, gold and platinum and industrial important metal like iron, copper, titanium belong to transition metal series. In this unit, we shall first deal with the electronic configuration, occurrence and general characteristics of transition element with special emphasis on the trends in properties of first row 3D transition metals along with preparation of and properties of some important compounds. This will be followed by the consideration of certain general aspects such as electronic configuration, oxidation state and chemical reactivity of inner transition metals. For the transition elements, D block 4.1 position of the position in periodic table. The D block occupies the large middle section of periodic table, flanked between S and P block. In the periodic table, the D block of penultimate energy level atom receive electron, giving rise to 4 rows transition metal, that is 3D, 4D, 5D and 6D. All these series transition elements are shown in table 4.1. 4.2 electronic configuration of the D block elements. In general, electronic configuration of outer these elements is n-1 d1 to 10 to ns1 to 2 except for palladium where the electronic configuration is 4d10 5s0. The n-1 stands for inner d orbitals with which may have 1 or 10 electrons, and outermost ns orbital may have 1 or 2 electrons. However, this generalization has several exceptions because of very little energy difference between n-1d and ns orbitals. Furthermore, half and completely filled set of orbitals are relatively more stable. A consequence of this factor is reflected in electronic configuration of chromium and copper in 3D series. For example, consider the case of chromium which has 3D 5 4s1 configuration instead of 3D 4 4s2. The energy gap between the two sets 3D and 4s orbital is small enough to prevent electron entering 3D orbitals. Similarly, in case of copper, the configuration in 3D 10 and 4s1 and not 3D 9 and 4s2. The state of electronic configuration of outer orbital transition element is given in table 4.1. 4.1 electronic configuration of outer orbital of transition element ground state. First series So this is scandium, titanium, vanadium, chromium, magnesium, iron, cobalt, nickel, copper, zinc, and this is atomic number, and this is 4s, number of electron in 4s orbitals, and number of electron in 3D subcell. So after these are important: chromium 3d5 4s1 and copper 3d10 and 4s1. These are two exceptions. And second series: terbium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. So these are atomic number, and these are electrons in 4d and 4s. Here you should learn this: palladium 4d10 contain 4d10 electrons. And 3d series: lanthanum, hafnium, tantalum, wolframum, rhenium, osmium, iridium, platinum, gold, mercury. Platinum and gold. Here gold is also an exception. Fourth series: actinium, rutherfordium, dubnium, seaborgium, borium, husmium, meitnerium, dumnostanium, roentgenium, and copernicium. Here is atomic number, and electron in 6d and electron in 7s. So here roentgenium, here is also an exception. The electronic configuration of outer orbital of zinc, cadmium, mercury, and copernicium are represented by general formula n-1 d 10 to ns2. The orbital in these elements are completely filled in the ground state as well as in their common oxidation state. Therefore, they are not regarded as transition elements. The d orbitals of transition element protrude to the periphery of an atom more than the other orbital, that is s and p. Hence they are more influenced by surrounding as well as affect the atom of molecules surrounding them. In some respect, ions gives dn configuration n is equal to 1 minus 9 have similar magnetic and electronic properties. With partially filled d orbital, these elements exhibit certain characteristic properties such display a variety of oxidation state, formation of colored ions, and entering into complex formation with a variety of ligands. The transition metal and their compounds also exhibit catalytic property and paramagnetic behavior. All these characteristics have been discussed in detail in this chapter. There are greater similarity in the property of transition element for horizontal row in contrast to the non-transition elements. However, some group similarities also exist. We shall first study the general characteristics of their trends in horizontal rows, particularly 3D rows, and then consider some group similarities. General property of transition element or D block elements. 4.3.1 Physical properties. Nearly all transition elements display typically metallic properties such as high tensile strength, ductility, malleability, high thermal and electrical conductivity, metallic luster. With the exception of zinc, cadmium, mercury, and manganese, they have no more typical metallic structure at normal temperature. Lattice structure of transition metals. So these are lattice structure from a solid state. This may be asked in NEET, but there is very low chance. The transition metal, with the exception of zinc, cadmium, and mercury, are very hard, have low volatility. Their melting and boiling point are high. Figure 4.1 depicts the melting points of transition metal belonging to 3D, 4D, and 5D series. The higher melting point of these metals are attributed to involvement of greater number of electrons from n-1d in addition to ns electron in the interatomic metallic bonding. In any row, melting point of these metals rise to give maximum at D5 except for anomalous value of Mn and magnesium and technetium fall regularly as atomic number of increases. They have higher enthalpy atomization as shown in figure 4.2. The maxima at about middle of the each series indicate that one unpaired electron in per d orbital is particularly favorable for strong atomic interaction. In general, greater the number of valence electrons, stronger is the result of bonding. Since enthalpy of atomization is an important factor for determining the standard electrode potential of metal with very high enthalpy of atomization, that is very high boiling point, tend to noble in their reaction. See later in electrode potential. Trends of melting point. So these are atomic number and here melting point. So titanium 3d series, titanium and chromium has highest melting point and then decreases up to manganese, then increases up to iron, and lowest is of copper. And in zirconium group 4 in 4d maximum melting point is of molybdenum and minimum of Ag. And in hafnium 5d maximum melting point is of wolframum means tungsten, and minimum is of gold. Another generalization that may be drawn from figure 4.2 is that the metal of second and third series have greater enthalpy of atomization than corresponding element of first series. This is an important factor in accounting for occurrence of such much more frequent metal bonding in compounds of heavy transition metals. Trends of enthalpy of atomization in transition elements. So here is atomic numbers and here is heat of atomization, and we can say this is 3d and this is 4d and this is 5d. 4.3 variation in atomic and ionic size of transition metals. In general, ion of same charge in given series show progressive decrease in radius with increase in atomic number. This is because the new electron enters in a d orbital each time the nuclear charge increases by unity. It may be recalled that the shielding effect of a d electron is not that effective. Hence, the net electrostatic attraction between the nuclear charge and the outermost electron increases and the ionic radius decreases. The same trend is observed in the atomic radii of a given series. However, the variation within a series is quite small. An interesting point emerges when atomic size of one series are compared with those of corresponding elements in other series. The curve in figure 4.3 shows an increase from first 3D to second 4D series of element, but radii of the third 5D series are virtually the same as those corresponding membrane of second series. This phenomenon is associated with intervention of 4f orbital, which must be filled before 5D series of an element begin. The filling of 4f must be 5D orbital result in regular decrease in atomic radii called lanthanide contraction, which essentially compensate for expected increase in atomic size with increased metal atomic number. The net result of lanthanide contraction is that second and third D series exhibit similar radii, that is zirconium 160 picometer and hafnium 159 picometer have very similar physical and chemical property, much more than that expected on the basis of usual family relationship. The factor responsible for the lanthanide contraction is somewhat similar to that observed in ordinary transition series and is attributed to similar cause, that is the imperfect shielding of one electron by another in the same set of orbital. However, the shielding of one 4f electron by another is less than that of one d electron by another, and as the nuclear charge increases along the series, there is fairly regular decrease in size of entire 4f n orbitals. The decrease in metallic radius coupled with increase in atomic mass result in general increase in density of these elements. Thus, the titanium Z is equal to 22 to copper Z is equal to 29. This is significant increase in density may be noted. Trends in atomic radii, transition elements, and here is radius. So from scandium to zinc radii decreases, and also in 4D and 5D. Electronic configuration of some other property of first series of transition element. So scandium, here is scandium, titanium, vanadium, chromium, magnesium, and cold nickel, copper, zinc, and here atomic number and electronic configuration. So there are two exceptions in electronic configuration. First, chromium 3d5 and 4s1, and copper 3d10 and 3d9. Enthalpy of atomization here. So first enthalpy of atomization increases, then it decreases, then decreases, then increases. So this is unsymmetrically. Ionization of enthalpy. So first IP increases, and second IP is maximum for second IP is maximum for this copper, and metallic or ionic radii in picometer is maximum for scandium. Standard electrode potential is this is maximum for copper, and density, maximum density exhibited by nickel and copper, and minimum density is of scandium. 4.3.3 ionization enthalpies. There is an increase in ionization enthalpy along each series of the transition element from left to right due to increase in nuclear charge, which accompanies the filling of inner d orbitals. Table 4.2 gives the value of first three ionization enthalpy of the first series of transition elements. This value shows that the successive enthalpies of these elements do not increase as steeply as in case of non-transition elements. The variation in ionization enthalpy along a series of transition elements is much less in comparison to variation along period of non-transition elements. The first ionization enthalpy in general increases, but the magnitude of increases in second and third ionization enthalpy of successive element is much higher along a series. The irregular trend of first ionization enthalpy of metal of 3D series along through little chemical significance can be accounted for by considering that the removal of one electron alters the relative energies of 4s and 3d orbitals. You have learned that when d block elements form ions, ns electrons are lost before n-1d electrons. As we move along the period in 3D series, we see that nuclear charge increases from scandium to zinc, but electrons are added to orbitals of inner subshell, that is 3D orbitals. These 3D electrons shield the 4s electron from the increasing nuclear charge somewhat more effectively than the outer shell electron can shield the one another. Therefore, the atomic radii decreases less rapidly. Thus, ionization energy increases only slightly along the 3D series. The doubly and more highly charged ions have DN configuration with no 4s electrons. A general trend of increasing values of second ionization enthalpy is expected as effective nuclear charge increase because one d electron does not shield another electron from the influence of nuclear charge because d orbitals differ in direction. However, in trend of study increase in second and third ionization enthalpy break for formation of Mn2 plus and Fe3 plus respectively. In both the cases, ions have d5 configuration. Similarly, break occur at corresponding elements in later transition series. The interpretation of various ionization enthalpy for an electronic configuration Dn is as follows. The three terms responsible for value of ionization enthalpy are attraction of each electron toward nucleus, repulsion between the electron and the exchange of energy. Exchange energy is responsible for stabilization of energy state. Exchange energies are approximately proportional to total number of possible pair of parallel spin in degenerate orbitals. When several electrons occupy a set of degenerate orbitals, the lowest energy state corresponds to maximum possible extent in single occupation of orbital parallel spin. Horn rule. The loss of exchange of energy increases the stability. As the stability increases, the ionization becomes more difficult. There is no loss of exchange energy at D6 configuration. Mn plus has 3d5 4s1 configuration, and configuration of Cr plus is 3d5. Therefore, ionization enthalpy Mn plus is lower than chromium plus. In the same way, Fe2 plus had D6 configuration and Mn2 plus and 3d5 configuration. Hence, ionization enthalpy of Fe2 plus is lower than Mn2 plus. In other words, we can say that the third ionization enthalpy of Fe is lower than that of Mn. The lowest common oxidation state of these metals is +2. To form Mn plus 2 ions from gaseous atom, the sum of first and second ionization enthalpy is required in addition to enthalpy of atomization. The dominant term of second ionization enthalpy, which shows unusually high value of chromium and copper, where M plus ion have the D5 and D10 configuration respectively. The value of Zn is correspondingly low, as the ionization causes the removal of one 4s electron, which result in the formation of stable D10 configuration. The trend in the third ionization enthalpy is not complicated by 4s orbital factor and shows a greater difficulty in removing an electron from D5 Mn2 plus and D10 Zn2 plus ion. In general, the third ionization enthalpy is quite high. Also, the high value of third ionization enthalpy copper, nickel, zinc indicate why it is difficult to obtain oxidation state greater than 2 for these elements. Although ionization enthalpy gives some guidance concerning the relative stability of oxidation state, which this problem is very complex and not amenable to ready generalization. 4.3.4 Oxidation state. One of the notable features of transition element is great variety of oxidation state. These may show in their compounds. Table 4.3 listed the common oxidation state of first row transition element. Table 4.3 oxidation state of first row transition metal. The most common one are bold type: scandium, titanium. So scandium oxidation state only +3, and titanium +2, +3 and +4, and +4 is most common. In vanadium +2, +3, +4, +5. In chromium +2, +3, +4 and +5 and +6, but +3 and +6 are most common. In manganese +3, +2, +3, +4, +5, +6, +7, but +2 and +7 is most common. In iron +2, +3, +4 and +6, but 2 and 3 are most common. And cobalt +2 and +3 and +4, but +2 and +3 are most common. In nickel +2, +3, +4, but +2 is more common. In copper +1 +2, but +2 is more common. Zinc +2 is more common. Only +2 oxidation state occur in zinc. The element which give greatest number of oxidation state occur in or near the middle of the series. Manganese, for example, exhibit all the oxidation state from +2 to +7. The lesser number of oxidation state at extreme ends stem from either too few electrons to lose or share scandium titanium, or too many electron d electron, hence fewer orbitals available in which to share electron with others. For higher valence copper and zinc, thus early in a series scandium second virtually unknown titanium 4 is more stable than titanium third and titanium second. At the other end, the only oxidation state of zinc is +2. No d electron are involved. The maximum oxidation state of reasonable stability corresponding value the sum of S and PD of manganese. And manganese titanium 4O2 and vanadium O2 and chromium O4 and manganese. This follow by rather abrupt decrease in stability of higher oxidation state. So that typical species follow Fe or Fe second and third, copper second and third, nickel only second, copper first and second, zinc only second. The variability of oxidation state or characteristic of transition element arises out of incomplete filling of d orbital in such a way that their oxidation state differ from each other by unity, that is uh, v v second, v third, v4, v5. This this is in contrast with variability of oxidation state of non-transition element, where oxidation state is normally differ by unit of 2. An interesting feature in the variability of oxidation states of d block element is noticed among the group 4 though 10. Although in p block element the lower oxidation state is favored by the heavier members due to inert pair effect, the opposite is true in the group d block. For example, in group 6, molybdenum 6 to wolfram 6 are found to be more stable than chromium 4, chromium 6. Thus, chromium 6 is more form dichromate in acidic medium as a strong oxidizing agent, whereas molybdenum trioxide and wolfram trioxide are not. Low oxidation states are found when a complex compound has ligands capable of pi acceptor character. In addition to sigma bonding, for example, NiCO whole 4 and FeCO whole 5, the oxidation state of nickel iron is 0. Name the transition element which exhibits only a variable oxidation state, does not exhibit variable oxidation state. So here is scandium. Zinc is not transition element. You should know this. 4.3.5 trends in M2 plus M standard electrode potential. Table 4.4 contains the thermochemical parameters related to the transformation of solid metal atom to M plus ion in a solution and their standard electrode potential. The observed value of E minus and those calculated using data table 4.4 are compared with in figure 4.4. The unique behavior of copper have the positive E minus account for its inability to liberate H2 from acid. Only oxidizing acid, nitric and hot concentrated sulfuric acid with copper, the acid being reduced, the high energy to transform copper solid to copper 2 plus aqueous is not balanced by its hydration enthalpy. In general, trend toward less negative E minus value across the series related to increase in sum of first and second ionization enthalpy. It is interesting to note that E minus for Mn and nickel and zinc are more negative than expected from the trend. So here observed calculated value of standard electrode potential M2 plus 10 to M naught element of element titanium to zirconium standard electrode potential. So standard electrode potential is maximum for copper. Here is observed value and calculated value. So observed value is greater than calculated value in copper, nickel and cobalt. Here are thermochemical data. First row of transition element and standard electrode potential for reduction of M second to M. The stability of half filled D subcell in Mn2 plus and completely filled D10 configuration in Zn2 plus are related to their E naught values, whereas E naught for Ni is related to highest negative delta hydration delta S naught. 4.3.6 trend in the M3 plus to M2 plus standard electrode potential. An examination of E naught M3 plus 2 plus values table 4.2 shows varying trends. The low value of scandium reflects the stability of scandium 3 plus, which has a novel gas configuration. The highest value of zinc is due to removal of an electron from the stable D10 configuration of Zn2 plus. The comparatively high value of Mn shows that Mn2 plus D10, D5 is particularly stable, whereas comparatively low value of Fe shows extra stability of Fe3 plus D5. The comparatively low value of fifth is related to stability of low value of vanadium is related to stability of V2 half filled T2G level. Unit 5 4.3.7 trends in stability of higher oxidation state. Table 4.5 shows stable highlights of 3D series in transition metals. The highest oxidation members are achieved in titanium X4 tetrahalides VF5 CrF6. The plus 7 state of Mn is not represented in simple halide, but MnO3F is known. And beyond Mn, no metal has trihalide except FeX3 and COF3. The stability of fluorine to stabilize the highest oxidation state is due to either higher lattice energy, as in case of COF3, or higher bond enthalpy in terms of higher covalent compound, that is vanadium F5 and chromium F6. Although a V5 is represented only by VF5, the only halide, however, undergo hydrolysis to give oxohalide VOX3. Another feature of fluoride is their instability in the low oxidation state, that is VX2. X is equal to chlorine, bromine, and iodine. Formula of halide in 3D metals. Oxidation numbers here plus 6, here plus 5, plus 4, plus 3, and 2 and 1. So CrF6 oxidation state of chromium is plus 6 and plus 5, presenting vanadium pentafluoride and chromium pentafluoride, and plus 1 oxidation state only occurs in chromium CuX. And applied to CuX. On the other hand, all Cu second halide are known except the iodide. In this case, Cu2 plus oxide I minus 2I2. 2Cu2 plus 4I form Cu2I2 plus I2. However, many copper first compounds are unstable in aqueous solution and undergo disproportionation. That is, 2 copper plus form 2 Cu2 plus copper. The stability of Cu2 plus aqueous rather than Cu plus aqueous is due to much more negative delta H hydration H naught of Cu2 plus aqueous than Cu plus, which more than compensate for second ionization enthalpy of copper. The ability of oxygen to stabilize highest oxidation state is demonstrated in oxides. The highest oxidation number in the oxides coincide with group number is attained by scandium trioxide and Mn2O7. Beyond group 7, no higher oxide Fe above Fe2O3 are known, although ferrate FeO4 2- are formed in alkaline media but readily decomposed to Fe2O3 and O2. Beside the oxide, oxocation stabilize vanadium 5 as VO2 plus, V4 as VO2 plus, titanium 4 as titanium O2 plus. The ability of oxygen to stabilize this high oxidation state exceeds that of fluorine. Thus, the highest Mn fluoride magnesium fluoride is magnesium tetrafluoride, whereas the highest oxidation state is Mn2O7. The ability of oxygen to form multiple bonds to metal its superiority. In the covalent oxide Mn2O7, each Mn is tetrahedrally surrounded by oxygen, including MnOON bridge. The tetrahedral MnO4 to power minus n ion is known as known for V5 chromium 6, Mn2 for 5, Mn6, and Mn7. Oxide of 3D metals groups oxidation number. So plus 7 only found in Mn2O7, plus 6 CrO chromium trioxide, plus 5 B2O5, plus 4 TiO2 B2O4 CrO2 MnO2, plus 3 scandium whole twice O3, and these are so on, and plus 3 only found in copper oxide. Would you account for increasing oxidizing power? So oxidizing power is directly proportional to this oxidation state of metals. 4.3.8 Chemical reactivity and E0 values. Transition metals vary widely in their chemical reactivity. Many of them are sufficiently electropositive to dissolve mineral acid, although a few are noble, that is, they are unaffected by single acids. The metal of first series, with the exception of copper, are relatively more reactive and are oxidized by 1 molar H+. Though actual rate at which these metals react with oxidizing agent like hydrogen ion is sometimes slow. For example, titanium and vanadium in practice are positive passive to dilute non-oxidizing acid at room temperature. The E0 values for M2 plus M indicate the decreasing tendency to form divalent cation across the series. This general trend toward less negative E0 value is related to increase in sum of first and second ionization enthalpy. It is interesting to note that E0 values for Mn, nickel and zinc are more negative than expected from the general trend, whereas the stability of half-filled D subcell D5 in Mn2 plus completely filled D subcell D10 and zinc are related to their E values of nickel. E0 values related to highest negative enthalpy of hydration. An examination of E0 values for redox couple M3 plus to M2 plus table 4.2 shows that M3 plus and cobalt 3 plus ion are strongest oxidizing agent in aqueous solution. The ions titanium and vanadium and chromium are strong reducing agent and will liberate hydrogen from dilute acid, that is 2 chromium 2 plus aqueous plus 2H plus aqueous form 2 chromium 3 plus aqueous plus H2 gas. Why E0 value of Mn3 plus and Mn2 plus couple much more positive than Cr3 plus to Cr2 plus and Cr2 plus to itna explain. Much larger ionization enthalpy of much Mn were required is 3D to 4D, mainly responsible for this. This also explains why the 3 plus 3 stress of Mn is little importance. 4.3.9 Magnetic properties. When a magnetic field is applied to substance, mainly two types of magnetic behavior is observed: diamagnetism and paramagnetism. Magnetic substances are repelled by supplied field, while the paramagnetic substances are attracted. Substances which are attracted very strongly said to be ferromagnetic. In fact, ferromagnetism is an extreme form of paramagnetism. Many of the transition metal ions are paramagnetic. Paramagnetism arises from presence of unpaired electron, each such electron having magnetic moment associated with its spin angular momentum and orbital angular momentum. For the compound of the first series of transition metal, the contribution of metal angular momentum is effectively quenched and hence no significance. For this magnetic moment, the determined number of unpaired electron and is calculated as spin only formula, that is mu equal to n under root n plus 2, where n is number of unpaired electron and mu is magnetic moment in units of Bohr magneton Bm. A single unpaired electron is magnetic moment 1.73 Bohr magneton. The magnetic moment is increases with increase in number of unpaired electrons. Thus, the observed magnetic moment gives useful indication about number of unpaired electrons present in the atom, molecules or ions. The magnetic moment calculated from spin-only formula and those derived experimentally for ions first row transition element given table 4.7. The experimental data are mainly hydrated ions solution or in solid state. Calculator observed magnetic moment, Bohr magneton, ion configuration, number of unpaired electron, magnetic moment, and these are calculated. So scandium 3d is 0, unpaired electron is 0, and in titanium unpaired electron 0, so magnetic moment is 1.73. तो इसमें ये देखेंगे अनपेयर्ड इलेक्ट्रॉन जितने हैं उसके मैग्नेटिक मोमेंट उसके आसपास आ रहा है। जैसे 2 है तो 2.84, 3 है तो 3.87, 4 है तो 4.90, 5 है तो 5.92, 4 है तो 4.90, 3 है तो 3.80, 2 है 2.84, 1 इज तो 1.87। पूरा कैलकुलेट करने की ज़रूरत नहीं है ऐसे। सो हेयर इज सम क्वेश्चन। Formation of colored ions. When an electron from lower energy d orbital is excited to higher energy d orbital, the energy of excitation correspond to frequency of a light absorbed. This frequency generally lies in visible region. The color absorbed correspond to complementary color of light absorbed. The frequency of light absorbed is determined by nature of ligands. In aqueous solution, the water molecule are the ligand. The colors of ions absorbed are listed in table 4.8. A colored solution of D block elements are illustrated in figure 4.5. 4.5 colors of some of first row transition metal ions in aqueous solution. From left to right, vanadium 4 plus, vanadium 3 plus, Mn2 plus. This is vanadium 4 plus, vanadium 3 plus, manganese 2 plus, iron 3 plus, cobalt 2 plus, nickel 2 plus, and copper 2 plus. Colors of transition first row elements and their ion. Scandium colorless, titanium colorless, titanium 4 plus colorless, titanium 3 plus purple, vanadium 4 plus purple, vanadium 3 plus green, vanadium 2 plus violet, chromium 3 plus violet, manganese 3 plus violet, chromium 2 plus blue, manganese 2 plus pink, iron 3 plus yellow, iron 2 plus green, cobalt 3 plus cobalt 2 plus blue pink, nickel 2 plus green, copper 2 plus blue, zinc 2 plus colorless. Formation of complex compound 4.3.11. Complex compound are those in which the metal ion bind to number of anions or neutral molecules, giving complex species with characteristic property. A few examples are FeCN6 3 minus, FeCN6 4 minus, CuNH3 NH3 whole 4 2 plus, and platinum chloride 2 minus. The chemistry of complex compound is dealt with detail in unit 5. The transition metal form a large number of complex compound. This is due to the comparatively smaller size of metal ion, their high ionic charges, and availability of d orbitals of bond formation. 4.3.12 Catalytic properties. The transition metal and their compounds are known their catalytic activity. Their activity ascribed to their ability to adopt multiple oxidation states and to form complexes. Vanadium V oxide is in contact with process, finely divided iron in hammer process, and nickel in catalytic hydrogenation are some of the examples. Catalysts are solid surface involved in formation of bond between reactant and molecule and atoms of surface of catalyst. First row transition metal utilize 3d and 4s electron for bonding. This has to effect increasing the concentration of reactant to catalyst surface, also weakening the bond of reacting molecule. The activation of energy lowering also because transition metal ion can change their oxidation state. They become more effective as catalyst. For example, iron third catalyst, the reaction between iodide and persulfate ion 2I minus H2O8 I2 plus 2SO4 minus. An explanation of this catalytic action can be given as 2Fe3 plus 2I minus 2Fe2 plus I2 and 2Fe2 plus H2OH 2 minus form 2Fe3 plus 2SO4 2 minus. 4.31.13 Formation of interstitial compounds. Interstitial compounds are those which are formed when small atoms like hydrogen, carbon, and nitrogen are trapped inside crystal lattice of metal. They are usually non-stoichiometric and neither typically ionic or covalent. For example, titanium carbide, magnesium nitride, and iron hydride, vanadium hydride 0.56, and titanium hydride 1.77, etc. The formulas quoted do not, of course, correspond to any normal oxidation state of metal. Because of nature of their composition, these compounds are referred as interstitial compounds. The principal physical and chemical characteristics of these compounds are as follows. First, they have high melting points, higher than those pure metals. Second, they are very hard. Some borides approach diamond in hardness. Third, they retain metallic conductivity. Four, they are chemically inert. 4.3.14 Alloy formation. In alloys blend metals prepared by mixing components. Alloy may be homogeneous solid solution in which some of one metal is distributed randomly among atoms in others. Some alloys are formed by atoms with metallic radii and within about 15% of each other. Because of similar radii and other characteristic percent of each other, because of similar radii and other characteristic of transition metal, alloys are readily formed by these metals. The alloys so formed are hard and have often high melting point. The best known are ferrous alloys. Chromium, vanadium, tungsten, molybdenum, and manganese are used for production of variety of steels and stainless steels. Alloys are transition metal with non-transition metals such as brass, copper, and zinc. Bronze, copper, and tin are also considered in industrial importance. सॉरी मेरे भाई, क्या हो गया यार, लग रहा है कि मेरी जान तूने मुझको पागल है किया, मेरा लगता ना जिया तेरा बगैर, तू मान मेरी जान. Some of important compounds of transition element. 4.4 Oxide of and oxoanions of metals. These oxides are generally formed by reaction of metal with oxygen at higher temperature. All the metals except scandium form MO oxide, which are ionic. Highest oxidation number in the oxide coincide with group number and attain AC whole twice O3 O3 to Mn2O7. Beyond group 7, no higher oxides of iron Fe2O3 are known. Besides the oxide, the oxocations stabilize V5 and VO2 4 V4 as VO2 and titanium 4 and titanium O2 plus. As the oxidation number of metal increases, the ionic character decreases. In the case of Mn2O7, the covalent green oil, even CrO3 and V2O5 have low melting point. In these higher oxides, the HD character is predominant. Thus, Mn2O7 give HMnO4 and